applications. Today in this session, we have four speakers, and first speaker is Dr. Pika Jha from NPL. Now I request Chinmay Shukla to start the introduction of Pika Jha ma'am.
Thank you, ma'am.
What to you, Chinmay?
Thank you. Hello, good morning, and a very warm welcome. I'm Chinmay Shukla, and I will be the host for today's session free lunch. And with me is faculty coordinator, Dr. Arpita Bhattacharya ma'am. I hope you all have learned something new and are enjoying this workshop from Amity Institute of Nanotechnology. As of today is the last day. I hope all these talks will encourage all the participants to attend to their curiosities by asking questions. So the first esteemed speaker is Dr. Pika Jha. Dr. Pika Jha received her PhD in chemistry from IIT Delhi, India. Currently, she is working as scientist F in solid state physics laboratory DRDO. Her research interests are in the field of carbon nanotubes and graphene. She is working on field emissions behavior of carbon nanotubes with focus on obtaining high current density from large area cathodes, as well as in the field of carbon nanotubes and graphene based devices. With special focus on sensors, she has 697 citations to her name and more than 40 publications in reputed journals. Her title for today's talk is Development of CNT-based Sensors for Environmental Pollutants. I request you, ma'am, to complete your talk in 45 to 50 minutes, followed by 10 to 15 minutes of question and answer sessions. So, ma'am, please.
Yeah, thank you, Chinmay, for your nice introduction. I would try to finish, in fact, earlier than that. It's really a great privilege and a pleasure to be able to speak to you and share some of my work with you. And to start with, I thank the organizers for having me as one of the speakers with you. So I come to the topic of my talk. I'll be speaking on carbon nanomaterials, development of electronic devices, but I would focus on sensors only today. So let's start the presentation. I am unable to go to the next slide. So,
Just,
yeah.
If you can.
Yeah. So now let me, since you all are from the, I guess, from the School of Nanotechnology of MIT. So I think you are well aware of the features that make any material a nanomaterial, or what are the deciding factors of nanotechnology. So by definition, the design and characterization and product application of structures, devices, and systems by controlled manipulation of size and shape at the nanometer scale that produces structures, devices, and systems with at least one novel or superior characteristic or property. So basically, even though we say that the size has to be less than 100 nanometer, often that is not the final criteria. The most important criteria for a material being graded as a nanomaterial is that it has to have one of the properties which is different from the bulk material. And of course, for a material to be classified as a nanomaterial, we must have a size, it must be man-made. So this also, I think the students of MIT will be well aware of, that the churches, the paintings on the churches which were made during the Roman times or later even in the Christian times, these churches had very colorful paintings, and all these paintings were realized by using different size of gold nanoparticles. So see, if we have a size of 25 nanometer and the color is red, and at 100 nanometer the color is yellow, which we normally see for gold. So these are so here we see that with the change of size, the color changes. So the technology of making nanomaterial was known to mankind long back, long before the actual term was coined. Only they didn't know that they were making nanoparticles. Even in India, we had carbon nanotube based swords, if you have read the history. So in India, we used to make swords which were known as Damascus swords, which were very flexible and the iron was actually impregnated with carbon nanomaterials or carbon nanotubes, and which were giving this kind of a flexibility, and also the kind of what should I say, the sharpness to the swords. Now, these are the two gurus of nanotechnology. One is Richard Feynman, and another is Eric Drexler. And you must be well aware of these two people, these who created the field of nanoscience and nanotechnology, as I can
We are
say.
not able to see
Now,
your screen moving. Ma'am, we're not able to see your screen moving.
which slide you are in right now?
You're in the first slide.
Oh.
You have to
So,
resume the.
should I stop share and
Yeah,
start
you can redo. Yes.
Ma'am, you can share your screen. Do not choose your PPT. You can choose only screen, because I think your office is old, so that's why it's not changing.
Okay. I will just do that. So is it okay now? I will remove the slide. Are you able to see it?
Still, it is in first slide only.
What about now?
Same, ma'am.
Ma'am,
Right now,
you have to choose your screen. Do not choose your PPT. When you're sharing, there is an option is coming screen. So you have to select screen, then share your slides. Do not select your slides. Do not select your slides.
I'm not selecting my slide. I am selecting share screen option only.
Then, ma'am, I think your internet connection is also poor, so that's why it's not.
That I am not sure. It could be that.
Your internet connection is poor, because I can see here it's coming. Your bandwidth is
I
very
think
low.
if you turn off your video and start sharing.
Yeah, I will do that. That's a better idea. Is it possible to see my other slides now?
We are still seeing your first slide only.
Same slide, ma'am. First slide only.
Ma'am, do not go to the slideshow view. Just now go this way, ma'am.
Now
Go
it is.
this way.
Now it is coming.
Okay. So now we see that nano technology has penetrated almost all the fields of our life, all the aspects of our life. And if you go to the future, it's in the not very far future, in the very near future, we will see that we already have integrated clothing with nanomaterials, which are wrinkle free, which are dust free, which do not get dirty. Then we also have we will have some piezo mats inside our cars to prevent vibrations on roads which are not so well paved. We will have electricity, photovoltaic that converts light into electricity. We will have even the menu cards will made of electronic cardboards. Each of one will probably, where we now wearing electronic watches, but we will have some electronic patches which will be made of nanomaterial based FETs. So we will just have to just paste it on our hands, and we will be able to measure all our body parameters and so many other things. It will be possible using nanomaterials. So the future of lies in the field of nanoscience and nanomaterials, and you people have made a very wise decision that you have chosen this as your career. Now coming to carbon nanotubes. You all must be knowing, being in the school of nanotechnology, that carbon nanotubes can be considered to be rolled up sheets of graphene. And there are two types of multi-wall carbon nanotubes, which are multi-walled and single-walled. And then the rolling direction of the carbon nanotubes actually tell us the chirality, and the chirality in turn tells us whether the carbon nanotubes are metallic or semiconductor, right? So my whole slide is visible to you?
Now it is visible, ma'am.
Okay, so the whole slide is visible now?
Yes, yes.
Okay. So now we know that when M and N, M is equal to N, then these are metals. So what are M and N? M or N are the units of the units of the unit vectors in the total chiral vector. So the indices of the unit vectors are known as N and M. So some carbon nanotubes are metallic while others are semiconducting. At least 2/3 of the carbon nanotubes are semiconducting. And mostly the metallic nanotubes are metallic, multi-wall nanotubes are metallic, because even if one of the concentric tubes is metallic, then the entire tube behaves as a metallic nanotubes. So 90% of the multi-wall nanotubes behave as metallic nanotubes. Now, coming to the applications of carbon nanotubes, there are several applications. Ranging from EMI shielding materials where graphene can be used, to structural materials where carbon nanotubes, they are already being used in many structural applications, in building the bodies of aeroplanes which fly high, like strategic airplanes. They are also used in tennis rackets. Then there are battery applications for energy storage and energy harvesting. Then there are photovoltaic applications also for energy storage and harvesting. Then there are flexible electronics in which graphene, then nanomaterials like molybdenum disulfide, tungsten selenide, all these are used. And memory devices also built on flexible electronics. Then there are biosensors, biomedical applications like drug delivery. You name an application and you can actually use the nanoscale platform to carry it out. So this is the number of US patents that have come up in the field of carbon nanotubes in the last few years. I have the data till only 2010. And if you see, there is an exponential increase in the number of publications for carbon nanotubes. So this exponential increase is not because just the researchers have just not chosen carbon nanotubes as their research material. It is because they have some unique properties which led to them. Now, coming to the carbon nanotube based sensors. First of all, let me ask you, what is a sensor? Are you aware about a sensor? What is a sensor? By definition, a sensor is an instrument that responds to a physical stimulus, or it could be a chemical stimulus also. Excuse me. So it collects and measures data regarding some property of a phenomenon, object, or material. And then the sensors are important part to any measurement and automation applications. The sensor is responsible for converting some type of physical phenomena into a quantity measurable by a data acquisition system. So basically what we do is we expose the sensor to some stimulus, and then we add it to a data acquisition system and a transducer, so that the change in the property of the sensor can be measured. So nowadays, each and every aspect of our life consists of sensors. You know, we walk into a room and automatically the lights come off, lights glow. And then when you go out of the room, the lights get switched off. That is based on a sensor. Then there are automated doors in many of the shops which are based on motion sensors. Then there are, see, in your cars, there are so many different types of sensors. There are pressure sensors, there are vibration sensors. See, the seat belt alarm is there. Sensor is very strong. The moment you sit, it starts beeping. So all these things, there are different types of sensors in our lives. So now coming to gas sensors. What are gas sensors? Basically, gas sensors are chemical sensors which give a change in some physical property which is measurable when a particular gas is the stimulus. So then if you want to have a gas sensor, what are the properties that you want to have? See, you want it to be selective to the particular gas you want to sense. Suppose you want to detect an LPG leakage somewhere. So that LPG leakage gas, LPG leakage will cause the gas to mix with the atmosphere. So atmosphere has so many different types of gases. They have pollutants and so many things. So if the sensor is selective, only then it should only detect the LPG. It should not detect any other gas which is present there. So this is what we mean by selectivity. Then it should have a response time. So if you want to detect some gas, the response time should be very low. Suppose it detects it at a stage when there is a lot of LPG in the room, or some pollutant it is testing, or some other flammable gas it is testing, and there is a lot of it in the room. In that case, what will happen? It won't be of any use. So it should be able to tell you that this is there in the room at a very early stage, so that you can take a preventive action. Then the sensor should be reversible. It should come back to its original state after the response has been taken, after it has given you the signal. So it should come back to your original state so that it can be reusable. Then, of course, from the industry point of view, there are issues like fabrication cost should be less and the energy consumption should be less. And then the sensitivity. The sensitivity should be very high. So the sensitivity is in turn related to the response time. The response time will be low only when the sensitivity of the sensor is very high. That is, it should react to a very gas. Now coming to why do we need nano sensors or CNT based sensors for that matter? See, the particles that are smaller than the characteristic lengths are associated with new chemistry and physics that lead to new properties that depend on size. So normally a material, a carbon material, you see the bulk carbon or the soot that you get, they would not tell you what kind of sensors it is. They can absorb the gas, but they wouldn't be able to tell you which gas it has absorbed. So that is why we need a nanomaterial, a carbon nanomaterial, because it will tell you, it will give you some change in its properties. That will tell you that there is some different gas present. Then when the structure is decreased, this is a very important thing. When the structure is decreased, the surface to volume ratio increases considerably. And therefore, what happens is a large amount of interaction volume is available to the incoming gas, which because of this, the sensitivity increases. And then the reduction of the sensing part or the transducer is important for miniaturization of the devices, as these days we are moving towards miniaturization. We don't want very big instruments. We always want something which is easy to carry, which is lightweight. So that is the focus of all the research that we are doing today. Then the science of nanomaterial leads with new phenomena, and new sensor devices are being built to take advantage of these phenomena. And as I said, the sensitivity can increase because of the large surface to volume ratio, as well as due to better conduction properties. And because of the better conduction properties in the nano size, the limits of detection can be lower and very small quantities can be analyzed, which can give you a lot of time to get into some preventive action. Now, what we are planning to make, people want to make an electronic nose out of a chemical sensor, and for that matter, from a nano sensor. So what is the difference between a human nose and an electronic nose? See, in human nose, the ordered analysis is superb. There's nothing which is there, nothing which is man-made, which can compare with a human nose. You know, so you can, yeah, so you can see that when we just smell something, we can tell it is a smell of a rose or it's a smell of a jasmine. So close smells we can tell, or something has rotten or something is cooking. So many things we can just, a simple nose, our nose tells us everything. Have we been able to mimic that in a man-made system? No, we haven't. So that is what we are trying to. So in an electronic nose, what we do is we try to coat the receptor with a coating layer so that it can be made sensitive to one particular agent. Now, how do you make an electronic nose out of it? So you have to have an array of sensors in which each of the elements of the array can be coated with a different material so that it will be sensitive to a different gas or a different compound. So this is what we are trying to do. So there are different types of, functional materials like which can have metals like gold, palladium, etc. Or we can have some specific polymers or some surface assembly materials. We can have all these things, and we can make it, sensitive to biochemical warfare agents, to explosives, because these two are very important from defense point of view. And for civilian point of view, we can make it sensitive to sewer gases and environmental pollutants and all these things. So I won't go into the details of these slides because I think I have almost explained all these in my previous slides. But I can tell one thing, that in this case, when you make an array, what will happen? You can functionalize each array of each nanotube with different functionalized material, and that will make you make these nanotubes very effective electronic nodes. So this is our aim right now. Worldwide, this is the aim, to make an electronic nose out of the artificial sensors that we are using. There can be different types of sensors, not only CMT-based sensors. There are sensors based on oxide also, metal oxide nanomaterial also. They are also being tuned to different applications to detect different types of reagents. Then there are surface acoustic wave-based sensors also. Then these are basically those sensors which can detect waves. And then there are some other bulky sensors based on IMS, ion mobilization, ion mobility spectroscopy. Then there are based on mass spectrometry. There are sensors based on gas chromatography. So there are different types of sensors, but all these are trying to achieve one single aim, that is to build an electronic nose, right? So now comparing these sensors will also show you that why personally I have chosen carbon nanotubes as one of my materials. Now there are some exceptional properties of carbon nanotubes which make them very lucrative choice of materials for sensors. The first of it is the high length to radius ratio, which allows a greater control over unidirectional properties of the material. What do I mean by unidirectional properties? See, that means the length to radius ratio is of the order of 1,000 or more, which makes it almost a pseudo 1D structure. So in the direction of the 1D structure, in the direction where you can consider the dimension existing, radial direction, you can consider the dimension to be 0. In that case, in the longitudinal direction, you can control the properties very effectively. And then they can behave as metallic and semiconducting, or insulating depending on their diameter, their chirality, and the functionalization or doping. They have a high degree of mechanical strength, so they are very robust, and they can withstand a large temperature range. So and they are in one way they are not they are chemically very stable. So when you expose them to the atmosphere, the CNTs don't change or undergo any chemical reaction per se. So these are stable materials, and then their properties can be easily altered by encapsulating other materials, and their functionalization can be done, and this makes them suitable for storing hydrogen or separating gases or sensing gases. And Amity has a very good group in this. Dr. Mittal has done some exceptional work using these encapsulating materials inside carbon nanotubes and using them as a sensing material. And now comparison of the gas sensors, which are normally which have been miniaturized. So there are 3 types of miniaturized sensors, like metal oxide sensors, then there are polymer sensors, and carbon nanotube sensors. Now there are advantages and disadvantages of all these types of sensors. The first thing is, in case of metal oxide, they are very low cost materials, and oxides are highly stable materials. Nothing happens to them in the atmosphere, and they have a very fast response time. The only drawback is that they have a high temperature operation. That is, you cannot have any response out of the sensors at a temperature below around 200 degrees centigrade. So even a minor fluctuation like opening the room where the sensor is stored will give you a change in the response. The response will be unstable in that case. Plus, this will give rise to more power consumption. In case of the polymers based sensors, the advantages is that they're highly selective and sensitive, but they're irreversible, and they are unstable over long periods of time. And then they get swollen in the environment when the environment is very humid. But in case of carbon nanotubes, the advantages is that in carbon nanotubes, every atom is on the surface. So the specific surface area is very high, and that makes a high surface to volume ratio, which in turn makes a high absorption capacity, and therefore they are able to detect gas up to sub ppb level, and their operation is at room temperature. They're environmentally very stable. So you would think that I'm trying to make you believe that everything is positive with carbon nanotubes. However, that is not the case, because if it was the case, then by now you would have had all the gas sensors or chemical sensors in the market based on carbon nanotubes. So there are certain disadvantages also of carbon nanotubes. So these are the issues which I will highlight right now. The first thing is that the repeatability of the device performance. See, when we grow carbon nanotubes, we really have no control over the material properties. That is, when we grow carbon nanotubes, the chirality is not under our control, the diameter is not under our control. So we have to resort to expensive sorting techniques, purifying techniques, and all these sorting and purifying techniques are bulky and costly. Not every fab line in a country like India would be able to afford them. Then there are purity and entanglement issues. If you have dealt with carbon nanotubes practically, you would know that they never exist as a single nanotube. They always exist as a bunch of nanotubes or as a bundle of nanotubes. So once you have a bundle, that very moment, the advantage of your high surface to volume ratio is lost, right? The effective surface area reduces. And then the purity, the entanglement or the bundle also is not repeatable from one bundle to another. So there is a problem about repeatability because of these bundles. Secondly, there are purity issues. When a grown sample you get the catalyst encapsulated inside the tube, then you have a lot of carbon impurities, which are non-carbon nanotube impurities, amorphous carbon impurities, and so many things. Then there are batch-to-batch variations, as I said, because the bundles will not be repeatable. So the chirality will not be repeatable. The amount of impurities will not be repeatable from one growth to another. Therefore, there will be batch-to-batch variations. So this is a very important issue. If you don't have a production line which can give you the same material over and over, then you cannot have an industrialization out of that product. Right. So this is one of the major problems why carbon nanotube sensors, in spite of having such unique properties, have not come into the market as of yet. Now there are some device processing issues also. See, do you know how we get carbon nanotubes? When we grow them, we get them as powders. However, when you grow something like silicon, you get it as a single crystal, which you can slice into a wafer. So all our electronics right now is based on silicon wafers, right? It's a silicon-based electronics. So it's a planar structure. The entire electronics that we have today is a planar structure. How do we incorporate a powder inside it? So, so you have to make this kind of a pellet out of it, and then you can slice the pellet. But using CNT, in spite of compressing it at a high temperature, if you try to slice it out, it doesn't work, it breaks. Okay. So then what do we have? We can then do some alignment between planar contact pads fabricated on pre-existing wafers. And then if you can see inside the circle, there is a very fine thread-like structure, which is a carbon nanotube, right? So you have to do something like that. And do you think this is easy? To separate one carbon nanotube and then place it between two electrodes in an aligned manner? No, it is not. It is very, very difficult, and there are only a few reports from groups like IBM and Caltech who have been able to do it. So this is not a industrial viable process. Therefore, it has not come into the market. Now, I will talk about CNTs as sensors for diverse analytes. Now, after discussing the advantages and disadvantages of CNTs, I will tell you are some of our work that we have done on using CNTs in the lab for sensing a large number of different types of, I would say, analytes or gases. Now, before I come to the results, I'll tell you the gas sensing mechanism. The mechanism is based on a charge transfer. When a gas comes and sits inside the nanotube, it gets absorbed onto the surface of the nanotube. Now, the carbon nanotube is, in general, a p-type structure. Because it has some absorbed oxygen inside it, that makes it a p-type. So when a p-type material is there, and then suppose a gas, which is a donor, electron donor, like ammonia, comes and sits on the surface. So ammonia has a lone pair of electrons. it can donate those electrons and CNT can accept those electrons. So what happens in a p-type, the majority carriers are holes. So when electrons come, there is a reduction in the majority carriers, which therefore increases the resistance or decreases the conductance of the nanotube. So this is a property that we measure, the resistance. When a gas, which is an electron withdrawing gas, it comes out and sits on the carbon nanotube. So what it does, it withdraws electrons from the CNT. So when it withdraws electrons, the number of holes increases, therefore the resistance decreases. So this is how majority of the gases are sensed using the carbon nanotubes. Now the amount of electron transfer varies from gas to gas. It depends on the electronegativity of the gas. So the change in resistance, amount of change in resistance will tell you which kind of gas it is. Further, if you consider, as I said, that the CNTs exist only as bundles. So in the bundles, there will be different sites on which the gases will come and sit. So I have indicated here the different sites where the gases come and sit. And then there is the binding energy, which is given through this, that the channels have more binding energy than the grooves, and then the pores, and last is the surface. So if a gas is small, which can get into the channel, then definitely it will have a more binding energy. So you will need more amount of stimulus to dissolve the gas, and the gas will also absorb faster. So that will give the change in resistance more quickly. So all these things will tell you which gas is coming and sitting on the surface, right? Now, how we have done it at SSPM. See, first what we have done is, initially this was our initial experiments in which we made a stable dispersion out of CNT, in which the CNT was dispersed into a solvent, alkyl formamide solvent, and then it was filtered over a membrane, a polycarbonate membrane, which is a polymeric membrane, and then we made some gold contacts on the surface, and in between the gold contacts we have the CNTs, and we take the contacts out of these from the gold, we put it into this kind of a header, and then this is a gas cell. This was our preliminary experiments, and this is the way we did the sensing. So we had 2 cylinders. The concentration was generated by using the mass flow controllers, and then it was taken into the gas cell. And then the desorption was done using a UV light, and the change in resistance was measured using a multimeter. The data acquisition could also be done on the PC. The mass flow controllers could also be controlled using the same PC. Now let us see the response of the CNT. By CNT TFR, here I mean CNT thin film resistors. So as I said, we disperse the CNTs in a particular concentration, and then we filter it out. So we made different concentrations of the dispersion. So these are the different concentrations of the dispersions that we have studied here. And then we poured them out onto the membrane, and we created the sensors as I had explained earlier. Now we see, as we increase the concentration of the dispersion up to a particular limit, we see that the change in resistance increases. That is, the response increases. But after a particular limit, when we from 1 to 5 mg per ml, we see that there is an increase in the response. However, Abhilasha, I'm in a lecture. And if we go below this, then we see that if we go beyond 5 mg per ml, we see that at 7 mg per ml, the response reduces. So when the response reduces, why does this happen? It is because the large number of metallic SWNT paths are created. Because when we go beyond a certain concentration, a large number of metallic SWNT paths are created. So the modulation happens only by the semiconducting SWNT. And since the metallic SWNT is created, so the change in resistance is lost. So the response reduces. Now, if we see what is the kind of response that we get. So I have here plotted the change in response from 0.5 ppm to 25 ppm for NO2. And we see that the response increases over the entire range till 25 ppm. And can you see the amount of response that we get at 25 ppm? This is huge, actually. At 25 ppm is not a very high concentration, but see the change in response. So this tells you that you are able to, even if you get a 1% response or even 0.5% response out of your nanotube, you know that this gas is present. So you know how much time you have to react to the leakage of the gas, to evacuate the population, to take some preventive action. Now you see here how much response we get in case of ppb concentrations of the gas. You know what is ppb? Parts per billion. Okay, so if we go from 50 ppb to 500 ppb, even in that case we have a response of about 1% to how much? To about 8%. So literally you will be able to detect in the ppb limits, parts per billion limits. So this is the kind of concentration, response that you get, and the kind of time you will be able to get before your concentration of the toxic gas reaches some lethal or dangerous limits, right? So you will be able to predict something is happening. Please clear the population out and let us do something about it. Now coming to the recovery of the gas sensor. The gas sensor is able to recover very fast, but however, initially we see that in the presence of only nitrogen, the recovery was not happening. The sensor used to give some response, but the entire of the NO2 gas was not getting dissolved from it. Therefore, it was not coming back to its baseline. So we tried different methods. We tried a halogen lamp. Again, then we found that there is not much difference in the baseline. Then finally, we did some thermal heating, and we said that initially the response was reducing very fast. However, after a certain limit, the response did not come back to a baseline. So finally, we did some UV measurements and we see that the response came back to the baseline. And after that, all the other exposures also gave almost the same level of response. So this was a very repeatable and useful form of recovery. Now coming to the effective recovery of the CNT thin film resistors. Initially, we see that after the recovery, we can, using the same concentration of the gas, we obtain the same response for repeated cycle of the gases. So now coming to another point, we see that if we do multiple exposures, then the rate of recovery changes. In the first, the rate of recovery is very fast. But as we keep on doing multiple exposures, the rate of recovery changes, as you can see from here. And if you see from here also, there is a minor difference in the slope of the recovery line. Okay, so the more the number of exposures, the slower the recovery becomes. That if you see here also, you will see that the recovery slopes are changing. Why is this? This is because there are okay, I'll come to the reason later. First, let me tell you this. Even the rate of recovery is faster at low concentration. At low concentration, almost for every exposure or for every the low concentration, the recovery rate is same. But as we increase the concentration, then the recovery rate falls. So this is why is this happening? This is happening because there are some reversible sites and there are some irreversible sites in the CNT. So the irreversible sites are those where once the gas comes and gets absorbed, it is not easy to dissolve them even with the exposure of the UV. So the gases, this is a small amount of sites, some 5% of the total sites which are there, which don't dissolve. So what happens is, after every exposure, every consecutive exposure, the amount of the gas which sits there will be there. It won't come out. So the more amount of gas will come at the irreversible sites, which are irrecoverable sites. So these will not get dissolved. This is why the change in slope takes place. Now, if we come to the repeatability and detection limit, we see that the repeatability of the gases are very, for the first cycle only, it is higher. Then from the second cycle onwards, it falls, but it remains stable after each consecutive cycle. This is because the same irreversible sites which are there, and then it gives a detection limit of about 127 ppt. That is, these sensors are able to detect up to 127 ppt per trillion of NO2, which is quite high. Now, if we do sensing in the presence of interference, suppose we do a mixture of gases. For example, we do ammonia and NO2. Then what happens is, as I said, that ammonia decreases the conductance while NO2 increases the conductance. So from that, we will also understand the response is opposite in case of ammonia and NO2. So if you do the NO2 sensing in the presence of ammonia, you see that the response decreases because of the effect of ammonia, which is mixed with the NO2. So all these factors have to be taken into account when we do a pattern recognition analysis of a gas, so as to identify an unknown gas, right? Now, how do we improve the selectivity? Because in the air, you will have both ammonia and NO2, and there will be many other oxidizing and reducing gases, right? So when you do a field sample, then you will have to do some improvement in the selectivity. But selectivity in case of NO2 is not like a lock and key arrangement that you functionalize it with a particular thing, and other gases will just be locked out and only one gas will be sensed. This doesn't happen. So what happens is that there is a change in the response after adding different types of groups onto the CNT surface. So here I have listed some of the groups that we have studied, like we have functionalized the carbon nanotube by carboxylic groups, which enhances the response of ammonia, reduces NO2. Then we have polyaniline also, which enhances ammonia and reduces NO2. Then we can do tin oxide nanoparticle functionalization. Then we can do another polymeric functionalization like Nafion. And all these will give you different behavior of the sensing. Now, now coming to some other gas sensors. For example, in Defense Ministry, we have to do some applications which are relevant to the Indian defense. So there are some chemicals which are called chemical warfare agents. These chemical warfare agents are of three types. They are blister agents like mustard gas, which cause skin blisters and then consequently death of army personnel. So then there are some chemical warfare agents which are like nerve agents, which actually attack your nerves and make your nerves very weak, and finally it leads to death. So basically it dysfunctions human beings' natural tendency to run for protection. And then there are several there are choking agents which stop spread breath. There are many different types of chemical warfare agents. So these days, these chemical warfare agents are more commonly used by anti-nationals and terrorist groups rather than for official warfare. But still, we need to protect our armed forces from these kinds of reagents. So, but chemical warfare reagents are not something which are easily available, and even not everybody is authorized to handle it. So normally the initial experiments are done based on some simulants. Is there anything that you want to ask, Chinmay?
No.
Okay. So basically what we have used is simulants. Simulants are those compounds which are not as dangerous but mimic some of the chemical properties of the actual chemical warfare agents. So here we have used dimethyl methylphosphonate, which is a simulant of the nerve agent called serine. Okay. So when we do the sensing of these simulants, we see that we have a very linear response from 24 ppm to 1200 ppm. And then you can see the repeatability of response at 1200 ppm. We get almost the same response of every consecutive cycle, and a very linear response from 24 to 1200 ppm. Even at 24 ppm, we get a very linear response, right? And then we have also done it to a lower concentration, like at around 500 ppb, which is 0.5 ppm. Here also we get some good response and a very linearity there also. So the response is 0.5% at 480 ppb, which is good enough to be, if it is good enough to be, detected or read out by your electronics, then this is also sufficient. Your electronics should be able to read the signal that the sensor is providing. So we have an electronics which can read 0.5%. So basically then we have a detection. We can actually start evacuating a personnel if there is an NDMMP exposure at 0.5 ppm also. So the detection limit is less than 69 ppb, right? And then these sensors, actually what we have done is we had functionalized it with a molecule called hexafluoroisopropane, isopropanol. So this hexafluoroisopropanol actually enhances the response as comparison to a bare CNT, which has not been functionalized. So this red one shows the functionalized CNT, and the black one shows the bare CNT without functionalized. And you see that how the response changes, how the response increases when you functionalize it, right? And then if you do a selectivity analysis, then also you see the how high the response is for your target analyte, which is DMMP, as compared to other chemical vapors, right? So this was one. Then there is another thing which is called explosives. Explosive sensing is also very important. These days, you know, you see whenever you go to a public place, you normally see a dog, a sniffer dog coming and smelling things, right? So this, they do it for the sensing of explosives. So till now, the most reliable sensing technique for explosive vapors is a sniffer dog. Okay, you don't have any electronic technique which is more reliable than a sniffer dog. The reason is that all of these explosives have a very low vapor pressure. So the amount of vapor that comes out and that would be sucked into a sensor is not sufficient to give a suitable response which can be read out by the electronics. So that is why we still rely on these sniffer dogs, but trying to do something so that we can reduce our dependence on these sniffer dogs. So we have started doing some sensing of DNT, and here we see that we have got some response of the DNT, though the baseline we get some good response, and the linear, there is a variation of response also. So this is you know, we have been able to sense till 88 ppm. So this is 88 ppm is the amount of vapor that we have generated using this DNT solid powder. So we are trying to improve upon this, and we are right now working on DNT as well as TNT explosives. And then there, as I said, there are some chemical warfare agents which are called blister agents, which cause skin blisters. So one of those is a mustard gas, and we have used a mustard gas stimulant, which is a dibutyl sulfide stimulant. And here also we see that we can detect 3.36 ppm of dibutyl sulfide with a response of 0.046%. So this also is a low response, though we have been able to detect it, but we need to improve it further. So this is also what we are working. Now, coming to another aspect of our work, which is development of a handheld prototype on using CNT. This is one of the important things, because I think I can claim this to be one of the first prototypes, fully working prototype based on a CNT gas sensors in the world, which has been demonstrated properly for NO2 and ammonia. So we have a patent, we have 2 patents regarding this. And here I can tell you how this works. See, I will also tell you how we have actually overcome some of the limitations of the CNT fabrication techniques that I had mentioned to you earlier. What is it? The first is coming to device fabrication. What we have done is, here we have taken an alumina membrane. Alumina membrane is 25 micron thick. So this alumina membrane, we have coated nitride on both sides. Both sides was fully coated with nitride. Since I can't go to the full screen mode, so I won't be able to show you the step-by-step method which I had here in an animated form. So I'll just explain it to you, since I can't show the animation here. So I'll just explain. So this gray is nitride, which was totally the blue aluminum. It was here. This entire thing was coated with a nitride. Then what we have done is, we have coated chromium and gold on top of it. Okay, on top of the nitride. Now, what we did, we first etched out the chromium and gold from some part of it using a photolithography and then etching techniques. We have etched out selectively some part of this chromium gold. Then below this, at another portion, we have etched out this nitride from the front side as well as from the back side. And then we filtered our dispersion through this, and the CNT was deposited at suitable positions on these this membrane. Using this, we have fabricated this membrane. This membrane has 60 devices inside it. Okay, 60 devices in a single membrane. And these are some of the devices which had been diced out of it. So you see there are 4 different devices in a single single sensor. So 4 different sensors in a single device. So the size of this device is 4 millimeter, 4 millimeter. So inside a 4 millimeter by 4 millimeter device, you have 4 different sensors, and here you have 8 different sensors. So basically the number of sensors that you have is equivalent to the number of gases that you will be able to sense. Okay. Now, if you consider this entire membrane, this is a 47 millimeter in diameter. So on a 47 millimeter diameter membrane, you have 60 devices, and for each device, for each of these dispersion, you have used only 0.25 milligram of CNT. Okay, so 0.25 milligram of CNT gives each containing 4 to 8 different sensors. So now you find out, see, so what we've done is we have obtained certain amounts of a repeatability in the sensors, because these sensors will be fabricated in a single batch. They will behave in a single way, single manner. Further, the growth problem of repeatability of the growth problem is also solved to a certain extent. In a single growth, you get up to 10 grams of CNT. So 0.5 milligram of CNT from 10 gram gives you a material repeatability over a large number of samples, right? So to solve the issues of repeatability of the fabrication process. So now these, once again, there are different types of configuration of the sensors which we have done. Now we functionalize each of these different sensors using a different functional group, and the unique signature, the cumulative signature that you will obtain will be unique, and that can be used for your pattern recognition or artificial intelligence algorithm to generate a pattern to identify and quantify an unknown gas, right? So this is how we mounted and take context, and then we have put it inside a gas cell. This was our first gas cell, right? And we have taken contacts out of it and put it in the gas cell. These are the outlets, inlets and outlets, and you can see the size of the gas cell. This gas cell was then loaded onto a PCB membrane. This PCB had a microcontroller based PCB membrane in which all the peripherals like the valves, the pumps, the UV LED, which was used for desorption, the mass flow controllers for everything was controlled using this microcontroller. Then we made this kind of a prototype. This was our first prototype which was made. This was made using 3D printing. And then we have a second prototype. We have named our prototype N Nasika. Nasika in Sanskrit means a nose, and N stands for nano. So now we have made this prototype, and this can identify and quantify NO2 and ammonia in on-field samples. This has also been extended for detection of ammonium nitrate. And here are the future directions that we are doing in future, some of the activities that we are doing for future. We have we are now using differently functionalized sensor arrays for detection of other variety of reagents. We have extended our studies to TNT, to RDX, and to different gases like sewer gases and some pollutants like SO2. And then we are trying to incorporate pattern recognition for quantification of unknown gases, other unknown gases in the field, so that it will be able to detect on-field samples for environmental pollutants. It can be taken inside the sewers because there are a large number of sewer deaths happening every year. So for personal safety. And we are also trying to integrate the CNT-based sensor technologies with complementary technologies for, making a redundancy there, so that both the technologies will give you some kind of data, and you will be doubly sure what kind of gas is there. So that is also something which we are working on. And thank you for hearing me out so patiently. I hope I have been able to convey what I am doing to you quite. I have tried my best. I hope I have been able to convey it to you, and you have understood or got a feel about some of the work that we are doing here at SSPL. And I would also like to acknowledge the contributions of all my team members, without whose hard work this would not be possible. And thank you.
Thank you so much, ma'am, for so elaborate discussion on the CNT-based gas sensors. Surely our participants gathered so much knowledge from your presentation. So thank you once again, ma'am.
Thank you.
Let's,
It's been a pleasure.
yeah. So really, it's a very elaborative discussion, and now we want to take the question from our participant. Is there any question? Chinmay, can you see any question?
Ma'am, there are no questions in the chat box, but yeah,
Yes.
there is one question. Okay, we have one question.
You can.
So the question is from Warren Rosario. So he says that can we use biological elements to functionalize nanomaterials to increase selectivity towards a specific gas?
Yeah, you definitely can do biological functionalizations also. There's no issue to it. There are several reports in the literature where biological materials have been functionalized over the CNT surface, and I think if you look into the literature, you will be doing it. But in essence, we don't. We have other labs who biological materials, so we don't want redundancy in the work here. So that is why. But you can definitely do it. Yeah.
And are there any disadvantages to this approach?
As I discussed initially, there are disadvantages of CNTs because the issues related to the fabrication and the material preparation. Initially, if you have seen this slide, I have listed out the issues that we have for the CNT based sensors. So that's most of the techniques are not scalable and industry friendly. But in our work, this is some of the issues that we have tried to address using our methodology, where we can at least have not a bulk production, but a semi-bulk production in which you can have 2 to 3 membranes prepared at a single go. So you will have some repeatability over, say in each membrane, if you have 60 devices, so if you can prepare 4 membranes at a single go, so you will have 240 devices, which will have quite some amount of repeatability inside it. The major problem is that scalability and the repeatability.
Yes,
So this is something that you have to address. And this is not an issue particularly to the CNT based sensors. This is an issue related to all nanomaterials. All the nanomaterials will suffer from the reliability and the repeatability issues.
ma'am, I have a question. What will be the cost related to these sensor development?
So see, if you have heard my presentation, I have used 0.25 grams of CNT for a single batch, right? So 0.25 grams of purified carbon nanotubes, single wall. So the purified carbon nanotubes, 2 grams of it I buy at a cost of say 1 lakh or something like that, right? 2 grams. But if you consider 2 grams and I have used 0.25. So can you 0.25 milligrams, right? So you can scale out the cost from there, right? 0.25 milligrams for 60 samples, 60 devices. Okay, so that comes out to be a very low cost. Further, the alumina substrate that we have used, that is about 50,000 for 50 substrates. So that is also very, very cheap. So, and the rest of the electronics and everything we have developed here. So I don't see it to be very costly device, finally. Right now it is only in a research scale. So once the research will be over, then it will be even cheaper.
And if the repeatability increases, then obviously the cost will go down for each.
Yeah, definitely. So this is what we are working at. We are trying to make the devices as repeatable as possible. So that is why we are trying to prepare more number of devices in a single go. We are trying to even reduce the amount of CNTs further, so that एक बैच में अगर 10 ग्राम आता है तो वो 10 ग्राम में हम जितने मैक्सिमम सैंपल्स बना सकते हैं उतना बना दें.
Ma'am, I had a question as well. So, ma'am, I wanted to ask, do this like when we are taking just the CNT, right? We are not functionalizing it. So like for specific gases, can we have like specific, for example, when we are talking about the resistance changes or the, so like, can we have like specific gases giving specific amount of current for
Yeah,
specific
definitely.
concentration?
Yeah, this I explained this when I said that will be dependent on the amount of charge transfer that will happen from one gas to the CNT, and the amount of charge of electron affinity of that gas with the CNT, right? So, for example, if I give you the example of NO2 and ammonia again, in NO2 withdraws 0.6 electron per molecule from the CNT towards itself, while ammonia donates 0.04 electrons per molecule towards to the CNT from itself, right? So the change in resistance will always be different for different gases. This is what you will use for your, pattern recognition algorithm or the AI. When you incorporate AI to identify a mixture of gases and quantify and identify which are the components of the mixture and in what amount, these are the parameters that you will be looking at. The change,
Right.
the difference in the response, and that will come from the difference in the amount of electron or the charge transfer that will take place.
Right, ma'am. Okay, ma'am. Then we have no more further questions. So let's thank ma'am for this wonderful talk on CNTs and how she managed to, bring the problems some solutions. So thank you very much, ma'am. And now we
Thank
can
you.
move on.
Thank you for having me.
Thank you so
and
much, ma'am. We want to
thank
hear
It's
from
been a
you
pleasure.
in
Thank you.
future.
Okay. Okay. Bye.
Thank you so much, ma'am, for your time.
Thank you. It's been a pleasure.
Okay, then now we welcome our next esteemed speaker, Mr. Bidan Das. So, Mr. Bidan Das is a Master in Science and postgraduate in Packaging Technology from IIP Mumbai and pursuing PhD in Flexible Packaging from Jadavpur University, Kolkata. Mr. Bidan Das currently is working as the Deputy Director and Assistant Professor with Indian Institute of Packaging, Kolkata, and acting as a head of the Eastern Regional Center of Institution of Packaging. He has almost 23 years of working experience in packaging and worked with different organizations such as Imami Limited, Kolkata, Radha Madhav Corporation Limited, Daman, Javeri Flexo India Limited, Silvassa, and Roto Packaging Materials Industry Company, Dubai, Akar Laminators Limited, Aurangabad, etc. He is a professional member of Institute of Packaging Professionals, USA since 2001. He is also a certified packaging professional from IUPP, USA. He has been guest faculty in Techno India College, Lady Bourbon College, Kolkata, National Institute of Fashion Technology, Kolkata and Shillong, and as a NHSM Knowledge Partner, Kolkata. He has delivered more than 250 lectures in different national and international conferences and seminars and workshops organized by various government and private organizations. I now welcome Mr. Bidan Das. And sir, I would ask you to please restrict the talk to 45 to 50 minutes, followed by a 10 to 15 minutes question and answers. Thank you, sir. The stage is yours.
Thank you, Chinmay, for a nice introduction. Yeah. Good morning to all of you. As Chinmay told, I will try to manage the time and let me try. Okay, so I'll be talking on basically the application of nano in the packaging. So I'll start with the packaging and introduction and then different techniques of packaging and then application of nano in the packaging. Okay, so I think before I start, there are a lot of students, I think, in this, in the participants and the audience. So let me give some introduction about the Indian Institute of Packaging or the career in packaging. Maybe somebody may be interested in this field. Okay, so as I told that it is the Indian Institute of Packaging, which is autonomous body in the field of packaging by the Government of India, Ministry of Commerce and Industry. This is our headquarters located in Mumbai. This is the Kolkata center where I sit. This is in Solid Sector 5 in Kolkata, West Bengal. Basically, we have the branches at different metropolitan cities like Delhi, Chennai, Mumbai, Hyderabad, Ahmedabad, and one more branch has started last year in what is called that Vizag, Visakhapatnam. Okay, there may be 1 or 2 branches is going to come up. One is in Bangalore under construction, and one more in northeastern branch that is in Guwahati. Calcutta branch is the second oldest branch. Started in 1971, no 73, and Chennai was started in 1971, and Mumbai established in the year of 1966. Okay, these are the different branches located at the different cities other than the head office. Basically, the packaging industry, IIP is giving a service to the packaging industry, basically to boost the export from our country. Our main functional aspect is to promote the packaging by the innovative design and development, and also to encourage the what is called that packaging industries for setting up or doing the innovation. And by giving an award, we also give an award that is the best packaging of the country, that is India Star Packaging Award. And also the packaging machine is awarded by the Pack Machine Award. Once in 2 years we are giving this award to the industries or the packaging manufacturers. And main function of IIP is to create the awareness about the packaging, and also we are a knowledge partner for the packaging knowledge or education. We have different courses we conduct. One is the 3-month certificate course, then 18 months diploma in packaging, and also 2 years postgraduate diploma in packaging, for which now that the application is undergone. Okay, now I think we also offer, now from this year onwards, we are giving the MS in packaging from Hyderabad center, that is from JNTU, and from Delhi we are giving the MSc in packaging, which is given by the Indraprastha University in Delhi. Calcutta and Mumbai still we are doing the PGDP, that is a postgraduate diploma in packaging technology, which was started in the year of 1986. This is now 38th batch, which is going to be admitted in the month of August. Other than that, we have also a lot of training programs, short-term, long-term, and also the testing services, which is one of the main function of the IIP. So we do test the packaging materials for the food, non-food, or consumer goods, whatever may be. So and IIP is authorized by the DG Shipping, Director General of Shipping, and Director General of Civil Aviation, for testing the packaging meant for dangerous goods. If there is any dangerous goods which are used to pack inside a packaging for export, so this packaging has to be sustainable, or it has to be withstanding the hazards which may undergo during the transportation of these goods, because dangerous goods are all what is called that injurious to the nation. So it may create any danger to the nation, so it should protect, the packaging should protect the goods. So that is the test we do, that is called UN certification. Basically it is called United Nations certification. Any dangerous goods, if it is exported by sea or by air, the packaging has to be tested and certified as per the norms laid down by the international norms, that is called IMDG, International Maritime Dangerous Goods, and also by the DGR, there is a dangerous goods regulation for IATA, that is Air Transport Authority. They are giving the mandatory testing parameters. So we do the test, and on successful completion of the test, we give a certificate. That certificate is called as a UN certificate. Without that, the goods, dangerous goods, will not be taken by the shipping line or by the airline to be loaded on the ship or inside the aircraft, because this may create accident. That Malaysian airline was vanished. Later on, it was found that this flight was containing huge amount of lithium ion battery, which is basically a dangerous goods. So more than the limited quantity, what is the restriction quantity, above the quantity, the flight was fully loaded with lithium ion battery, and this might be one of the cause for losing the connectivity with the air traffic control, and the flight was vanished and a lot of people died. So this is one of the reasons why the dangerous goods need to be tested, and the packaging has to be as per the regulation by the committee of experts for the dangerous goods. And our laboratories are accredited by the NABL and also BIS, that is a Bureau of Indian Standard, as per ISO 9001 2015 for the system management certification, and NABL, that is ISO 17025 for the as per the your international norms, that is called NABL, National Accreditation Board of Testing and Calibration Laboratories. And even for the food testing, in any food packaging, when it is packed as per the FSSAI guideline, this packaging also has to be tested as per the NABL from any of the laboratory. And we also have to provide the consulting services for design development and value addition, or even the value engineering for the packaging. We give a lot of consultancy to the industries and also to the government departments. Like we have given a lot of consultancy to the the government departments, like all the commodity boards, EPIDA, MPDA, Spices Board, Tea Board, Coffee Board, and many more. And also MOAPI, that Ministry of Food Processing Industries, Government of India. Then also Coconut Development Board. So whatever the different innovative products they're manufacturing, so how the packaging has to be done, we have given the consultancy to the departments. More than we also provide the technical audit, or the company we do visit and give a advisory report that what improvement can be done in the packaging. Under the research and development, we are also doing a lot of innovative packaging design development, and also the shelf life evolution for the different food products. That's all about the institute. Now coming to the packaging industry, if you see, the packaging industries are classified into three categories, like raw material manufacturing, packaging material converters, and packaging user industry. These three industries are termed as the packaging industry. Now if you see, what are the materials, or what is called the packaging raw material manufacturing industry? So now if we go into that, so we should know what are the different raw materials used in packaging. If you see, their packaging materials are classified into two categories based on the the sources of manufacturing. One is called scientific packaging material, another is called traditional packaging material. What are the scientific and what are traditional packaging materials? Now if you see, scientific packaging materials are paper, glass, metal, and plastic. These four are termed as scientific packaging material. Basically, there are a lot of development happening in the plastics for the nanotechnology. Other than that, paper, glass, and metal, these three, and this plastic, these four are called as scientific packaging materials, which are scientifically manufactured and produced by the industry. And other than that, there are few materials which are called as a traditional packaging materials, like earthen pot, bamboo basket leaves, wooden barrel, and jute bags. These are all traditional materials which are taken from the ecosystem and used. So there is no scope of using nanotechnology in this traditional packaging material. Yeah, definitely in scientific packaging we can use the nanotechnology, and a lot of development is happening, though there is not much commercial availability of the nanotechnology used in packaging. But there are in the recent trends, like the intelligent packaging and the active packaging, there are a few examples of nanotechnology being used in packaging. Now if you see what I told, the packaging raw material manufacturing company. Now this scientific packaging material, paper, glass, metal, and plastic, the industries or companies who are manufacturing these materials, paper, there is a paper mill, or glass manufacturing industry, or even the metal or plastic granules, they are termed as the packaging raw material manufacturing company. And these raw materials like paper, glass, or metal, or plastic, which companies, they are converting this into the packages. Like say, I give example, this Reliance Industries Limited, they are manufacturing polymer granules, like all these plastics, polyethylene, polypropylene, or even polyester, nylon, all these things. So they are manufacturing the granules, raw material. So they fall under the packaging raw material manufacturing industry. Now there are companies who buy this raw material from these raw material manufacturing companies, and then they convert this into the packages, like say plastic bottles manufacturing company, plastic jerry can, plastic drum, and all these things. Or even say some paper mill like ITC Bhadrachalam, they have a paper mill manufacturing the good quality of paper. So they fall under the packaging raw material manufacturing company. Now there are industries who are buying this paper board and doing the printing and coating, and then making the board or boxes for using. Like in lot of specialty coatings and printing inks are using nanotechnology, because of the good coverage, that is the yield will be high because of the low particle size and bigger surface area. In the coating and varnish industry, a lot of nano is been used. And the third category of industry is called as the packaging user industry. User industry means the companies or the industries who are manufacturers of the products. So to pack their product, they need to use the packaging material. So this user industry, they will buy the packaging materials from the converters. Converter will buy the raw material from the raw material manufacturing companies. So what I want to mean that all these three industries, their development, their growth is depending one upon each one is dependent on another one. So if the raw material is scarcity, then they cannot supply to the converters, and converter cannot produce the goods, and they cannot supply to the user industry. As a result, user will suffer. So all these three industries are running in a closed loop, and each one is dependent on another one. So these are the three segments or packaging materials manufacturing companies. Now, what are the, I told you scientific packaging materials, and then there are few materials which are termed as ancillary packaging materials. What are the ancillary packaging materials? So ancillary packaging materials are basically the materials which are not the main packaging materials, but without the help of this, the packaging operation cannot be completed. Like if you see the close caption closure, like if I pack something in a glass bottle or a plastic bottle, so the bottle is the main packaging material, but the bottle need to be closed with a closure. So the closure is a ancillary packaging material. Or even if you see a glass bottle is packed with some perfume or some liquid or some other products, the tomato sauce or something like that. So the glass bottle, what is inside, how to communicate with the consumer, we need to put a label. That is, the bottle is very difficult to print, so we need to put label on the bottle. So label is another ancillary packaging material. So the packaging material means these are not the main packaging material, but without the help of this, the packaging operation is not able to be completed. So that is called ancillary packaging material. These are all supporting materials which are need to be completed. They are providing support for completion of the packaging operation, like BOPP self-adhesive tape. It is a small corrugated box or mono carton. How to close this? So to close this, we need a BOPP self-adhesive tape, or sometimes stretch film or cling film for closing the boxes or wrapping. In the rainy season, when you get something by the Amazon or Flipkart or any other e-commerce media, we get the box which is wrapped with a plastic film, that is called as a stretch film or cling film. Then straps, clips, hooks used in the wooden boxes or corrugated boxes, bubble films, then thermocol, then other cushioning materials which are used for the fruits and vegetables, like there is a what is called the jacketed foam used for the apples and other things. So these are called as a cushioning material which are used for the packaging or wrapping of the products. Like you see this is a what is called the polyethylene foam, which is used for the fruits and vegetables. So this is called as a cushioning material, which is a polyethylene foam used as a cushioning material to cover up the fruits, to give them a protection from the damage during the transportation. So now again, depending upon the nature of packaging materials, packaging can be classified into 3 categories. That is depending upon the flexibility of the materials. So the materials which are have their own size and shape, even they are empty, they cannot be reduced in sizes. Like the glass bottle, if you see a glass bottle, even or plastic bottle, if the no product is there inside the bottle, like this is a PET bottle. If something, there is a product, if product is not there also, we cannot make this bottle in smaller, or say this is a HDP bottle. So even empty, this nothing is there, we cannot reduce the size. So these type of packaging materials are termed as rigid packaging material, like glass bottle, metal container, plastic container. Like if you see this is a sample, this is a spray. So this is a metal container, even nothing is there inside, the bottles or the can cannot be reduced in size. These type of materials are termed as rigid packaging materials. Then flexible packaging materials are the packaging materials which can be folded when the product is not filled inside the packages. So they require lesser space in the empty condition, that is empty packaging materials. So when they are transported, they require lesser space, and also the weight is less. So as a result, they cost less in transportation and distribution. And any material which is lighter in weight, definitely the cost also will be less. So flexible packaging is the most economical packaging materials, like sachets, laminates, pouches. These are called as a flexible packaging. And then semi-rigid packaging is basically a duplex board carton, which is called as a semi-rigid. Like if you see this carton, this is a carton, mono carton. I just take out the product from inside. Then what we can do, we can make it as a flat. No, it got reduced in size. If you want to pack it, we close it, the flap, and then we put the product inside. So this type of packaging is called as a semi-rigid containers. So semi-rigid is basically made up of paper, and a little bit of plastic boards are also available. Now all these packaging, depending upon the function of the packaging, they are considered classified into 3 categories: primary packaging, secondary packaging, and tertiary packaging. What is the primary packaging? The first packaging around any product is termed as primary packaging, and then secondary, and then tertiary. So the packaging for, if you see this picture, the first level of packaging is termed as primary packaging, and then the packaging for primary is called as a secondary packaging, and then packaging for the secondary packaging is termed as a transport packaging, or it's also called as a shipper. Shipper means this helps the product for shipping or transportation or distribution. So that is called as a shipper. Normally we call as a transport packaging. There may be some other level also, depending upon the type of customers. Packaging can be classified into 2 categories, like one is a consumer pack, another is called industrial pack or bulk pack. Consumer packaging is basically the packaging which will ultimately reach to the consumer from the point of sale or merchandising outlet. And industrial packaging is basically a pack which contains huge quantity of goods and is basically supplied from one manufacturer to another manufacturer for further processing. Like if you say a pack of 1 liter of water, or 2 liter or 5 liters of water, these are all consumer pack. Like even small bottles also there, like 200 ml also there, which is given in the aircraft. So these are called as a consumer package. Now there is a pack of 20 liter water which is packed in a we call as a bubble top container. So that is basically called as a bulk pack or industrial pack, which is basically a big pack or a pack which contains huge quantity and not for consumer. It is basically further used for further processing, like in the tea shop or restaurants, they are making tea, coffee out of this water. They use this bubble top container. Or even if we say we buy a packet of atta or maida which is 1 kg or 2 kg or 5 kg for a domestic application, that is called a consumer pack. And then if a hotel, restaurant, or even other institutions who are say running a catering services and all these things, they might be buying atta, one bag is 100 kg or 50 kg in one bag, jute bag. That is called as an industrial package. So industrial package is basically the bigger quantity, means more quantity inside a pack for further processing, and it is supplied from one industry to another industry for further processing. And the consumer pack will basically it reaches to the ultimate consumer. This is called as a consumer pack. So if you see the FSSAI guideline, the consumer packaging, the mandate is different for labeling and display. Even for the industrial packaging, the mandate for labeling is different. And consumer pack must follow the Consumer Protection Act as per the Consumer Protection Act of Government of India. And also, if you see the FSSAI guideline, the Act of Food Safety Act, for the consumer packages, the labeling is different. For industrial packaging, labeling requirement is different. And there may be also sometimes further levels of packaging, depending upon the product and the type of distribution and all these things. So the first level of packaging is termed as primary packaging, then secondary packaging, then tertiary, quaternary. Fifth level is called pentary, and the sixth level of packaging is called as a hexary level of packaging. So these are all the different levels of packaging, and the level which will ultimately reach the consumer is termed as the the consumer pack. If you see this pack, this is basically for a photographic film which is used in the earlier days, and in this pack, the tertiary level of the packaging, which is basically procured by us from a studio or from a shop. So this is termed as the consumer pack. So in this picture, the tertiary packaging is the consumer pack. Like in case of toothpaste is coming in a tube, then tube is further put inside a mono carton. So that is the secondary packaging is the consumer pack. So every time primary packaging may not be the consumer pack. So it depends upon the type of product and the the nature of packaging material. Normally the 90% of the time, maybe we see the primary packaging becomes the consumer pack, but sometimes it may vary also. Now, these are the market share of the different packaging materials. If you see globally, there are 30 to 34% packaging materials is paper-based material used in the all over the country, all over the globe. Basically, this is rigid plastics is 27%, glass 11%, flexible packaging 10%, beverage can there is aluminum or tin can, it is almost 6%. Other metal, there is a tin plate container 9%, and others is 3%. So this is the market share of the different packaging material across the globe used for. And if you see almost 80% packaging is used by the food and beverage and healthcare industry. This for the food and pharmaceutical occupies almost 80% of the market for the packaging, and other industry occupy almost 20%. So in packaging, basically in the food industry or in the healthcare industry, there is a huge opportunities of packaging. So there is a huge demand of packaging materials in all this industry. Like this is one of the example which IIP has developed a product. Basically, this is a village product. Basically, it is a manufactured by the the farmers or even in the small industry, very small. That is a home cottage industry type of thing. This is a liquid jaggery which is packed normally in the earthen pot, where we have developed a packaging of scientific packaging material. This is a what's called the plastic laminated tube used for packaging of the Nolen gur. And in this pack, the shelf life is increased, and all these regulation, it is obeyed by the regulations like Food Safety Act. Here, if you see, the thing is mentioned, so it does not follow the Food Safety Act. Like these are the developments which we have done under our R&D. There is a Nolen gur liquid jaggery for Government of West Bengal. We have done this packaging design development. Complete R&D was done by us and given to the Government of West Bengal. Now, if you see how much cost is involved in packaging, so basically, if we frankly speaking, there is no formula by which we can say, okay, this is the product, so this will cost this much. So there is no thumb rule from which we can come to know about the cost of packaging. But these are all again depending upon the the target customer you are looking for and the nature of the marketing perspective. So if you see one product, I just give example, say this is a salt, catch salt. It is made by Dharampal Satapal, is Delhi based company. So they are selling this salt at, say, I think 200 gram is cost 30 rupees, so 150 rupees per kg. Or if you see the normal salt is selling at the rate of 20 rupees per kg. So this same product in two different types of packaging. So this gives a customer basically the convenience, and the customer perception also different. So depending upon the customer, the cost the packaging cost may vary, and we may target different customers. So frankly speaking, there is no formula from which you can say this packaging cost for a particular product will be this much. So there is basically no rule also. So we can pack as much as required, but definitely the different customers, we are looking for the different consumer groups, and their buying power is different. So same product may be packed with different materials, and which will cost different also, and give the different convenience to the customer, and customer will be paying for that. Mostly whenever we do any packaging, we see the customer convenience and the type of customer which we're looking for. Now if you see the packaging industry, this is the the glimpses of that. The packaging industry is considered one of the 9th or 10th biggest industry across the globe, and it is growing at the rate of 5 to 6% in our country. The growth rate is more than 10%. In the Asia Pacific region, or in the whole world, packaging growth rate is 5 to 6%. Basically the growth is European countries less, but in the third world countries, China, India and other countries, the growth of the packaging industry is very high, double digit figure, 10 and above, and it's employing more than 5 million people across the globe. So more than 5 million people are working in the packaging as a career in packaging. Then it is valued more than, I think this year it is crossed 1,000 billion US dollar. And the companies in organized sector, there are more than 1 lakh of companies in the packaging which are organized. There may be many companies who are not in organized sector. Organized sector, there are almost more than 1 lakh company across the globe which are organized companies in the field of packaging. These are some examples of a traditional packaging which are used for our food and other application. I think these are all the scientific packaging material used for the these are called as a traditional packaging material for fruits and vegetables. This is also natural material, so these does not create any problem with the ecosystem. But again, more and more natural packaging we are using, again we are cutting the forest and creating deforestation, so we have to use scientific packaging material. This is some the packaging material which is used or developed by IIP for the packaging of pineapples. Pineapples was wrapped with the breathable film and then packed into the corrugated boxes which have the holes for breathing. These are all called ventilation holes, which require for breathing of the fruit or any horticulture produces. And this is the what I told you, the foam is used to keep the protection to the skin of the fruit for getting damages or spoiled. And this is basically two types we did, and we did the shelf life evaluation. We found that the pineapples can also be stored almost 25 days in the ambient condition, normal condition, without any cold storage. And this pineapple has to be plucked at the mature stage before it becomes the yellowish. We did this project for government of Tripura, and it was found that 25 days the pineapple shelf life is in the normal condition. With this type of packaging, it can be exported also. I think this is already covered. These are some of the flexible packaging examples. This is called blister packaging, which is basically as a semi-rigid type of packaging used for milk and all these things. This is rigid packaging, which is a glass bottle with metal closure. So metal closure, and this level is ancillary packaging material. Glass is the main packaging material. These are plastic. This is a metal containers used in packaging of tea or spices or any other food product. Even the coffee or milk powder can be also packed. And metal, by the property of the metal, because of the impermeability of the metal, it is basically providing the maximum shelf life for any product. If you see, if we pack in a metal, the shelf life will be maximum, because the metal is complete impermeability, because it does not allow any light to pass through, it does not allow any moisture to pass through, or it does not allow any gases to pass through the containers. As a result, any product, if we pack with a metal, that is giving a shelf life, the maximum shelf life. If you see some milk powders and other thing, the shelf life is given 36 months, which is also as per the FSSAI guideline, 36 months, the maximum time period for keeping any product under the shelf. Okay, these are some secondary packaging of butter, Amul butter and all this. These are some bulk packaging used for export of chemicals and all these things. This is called FIBC, flexible intermediate bulk container. It's a woven sack of polypropylene or HDP fabric, and then it is made into or stitched into a bag, and it can carry 1,000 kgs of the product for export and other things. These are termed as a FIBC bag, that is a flexible intermediate bulk container. This is the structure of one packaging which is termed as the retort packaging. Retort packaging is one of the innovative packaging for the ready to eat food market, which we know that earlier days only metal can was used for packaging of the ready to eat food, and metal become costly because of the the material and the technology also involved with that. So the retort packaging was not sold much earlier days. Now it has been developed in a flexible packaging, and the cost has come down when a metal can is costing 20 rupees, this type of pouch will cost almost 4 to 5 rupees. And as a result, the total cost of the packet will come down. And consumers nowadays are also buying a lot of ready to eat food. Like if you see, there are MTR foods on Pioneer, then ITC is there, Haldiram is there, who are doing their business in the ready to eat food market. And this is the global structure which is used almost by all the countries for packaging of the ready to eat food. Cooked food is packed inside the pouches, and then it is given a thermal shock for killing the bacteria or microbes, and this is called as retort pouch. So this is structure. Outer layer is a polyester, inside is a aluminum foil, then nylon, then polypropylene. So polyester, then nylon, then aluminum foil, then polypropylene. Polypropylene is the inside layer, because when the high thermal shock will be given to the pouches, polyethylene become prone to get melted, because the melting point of polyethylene is 120 degree, whereas the polypropylene will have melting point more than 140 degree. Normally the retort temperature in the retort is given 120 to 130 degrees centigrade temperature. So at this temperature, basically the polypropylene will not get melted. So this is safe of condition in contact with the food. And as it is a cooked food, so definitely this packaging material must be food grade as per the FDA or international law or even our FSSAI. This is a structure of a Tetra Pak. Tetra Pak, basically, we know that fruity and other thing is called a Tetra Pak. So Tetra Pak, basically, this is a 6 layers are there inside the packaging. The outer layer is the polyethylene, then it is a what is called that paper, then polyethylene, then aluminum foil, then polyethylene, then one more polyethylene. So this number 2, number 4, and number 5, number 3 and number 5 layers are termed as a tie layer, which is called as a binding layer. So outer layer is a polyethylene, which protects the paper from getting damages while it is stored in the fridge or in the ice. Normally the people used to have cold condition, the juices and all these things. And second layer is a paper, which is very good printing characteristics, and it can be printed attractive or beautifully aesthetically. Third layer is aluminum foil, which is basically, third layer is a polyethylene, which is called as a tie layer. Basically, it is an adhesive layer which is binding this paper, and the fourth layer aluminum foil. Aluminum foil is giving the barrier. Normally, in case of Tetra Pak, the aluminum foil thickness will be 25 and plus, so it is giving a complete barrier, no passage of air or moisture through the film. As a result, the Tetra Pak products are not need to store it under the refrigeration, and it can be kept under the shelf in ambient condition, and shelf life gives this thing. And this is called as a active packaging. Normally this application of nano or other thing is coming in our active packaging and intelligent packaging. Now what is active packaging? So active packaging basically is a technique which is basically called inside a pack, if other than the product, any other things, if we keep in smaller quantity to extend the shelf life of the product, that is called the active packaging technology. Active packaging is basically, other than the product, some external material will be kept inside the pack, and objective is to increase the shelf life. Very normally whenever I give example, whenever we buy any leather shoe, in the shoe box we find a small sachet of silica gel. So this silica gel is not our product, it is basically shoe is our product, but the silica gel is other than the product. So it is called as a active packaging material, which is basically the function is to absorb the moisture inside the box. So otherwise leather becoming hygroscopic, and it may absorb more moisture and it gets deteriorate, or fungus will be there in the rainy season. Like if you see the packaging of carbonated drinks, it is basically the sugar syrup for carbon dioxide is given. So CO2 can be considered as an active ingredient in this, and it is acting as an active packaging material, because CO2, when we punch in the carbonated drinks, it forms the carbolic acid, and any mild acid is acting as a bacteriostat in the food. So it will not allow any formation of microbes in the drinks. So this carbon dioxide forming the carbolic acid, and this is acting as an active packaging ingredient. Like this, there are so many other products also where the active materials are used. Even if you can say also, like say the potato chips packed in a nitrogen flushed pack. Here nitrogen gas is given, it is not a product, it is our product is a chips, but this can be considered as a active packaging material, which is basically not allowing the chips to get broken, and also it is increase the shelf life by eliminating oxygen inside the packaging, because if oxygen is there, it may get rancid, and the chips will not be consumable for the human being. So active packaging basically is that. And there is one more term is called intelligent packaging nowadays. So what is the intelligent packaging? Intelligent packaging is something extra what the normal packaging does. as we know from the word meaning intelligent. Intelligent is basically something extra than the normal sense. Normally, as any human being, we have 5 senses, we have 5 sense organ. But if somebody have some extra sense, he is or she is termed as an intelligent boy or intelligent girl. Okay, so intelligence is a different. So if we see the normal packaging is function is to provide, contain the product, then protection from the environment or protection from the transportation hazards, then communication, and then marketing, and all these things is called as a basic function of packaging. But other than this, if something extra that packaging can offer, then we term this as intelligent packaging. Like if you see, normally any food package, we found that is written as a shelf life, or it is written as a best before. And now I think FSSAI is changing the mandate also. They will write from the 1st July onwards that use by date. The food has to be mentioned as a use by date. Like if in some cases, normally in the frozen food, if it is mandated that it need to be stored in a -18° temperature, -18°, or say alcoholic drinks people are keeping at a low temperature, or even the milk, pasteurized milk supposed to be stored below 8°C temperature, that milk. Now if sometime the shop, the freezer is not working, or something happened to the shop and current went off, and then there is a load shedding long, so the temperature went up again, maybe after 4 or 5 hours, the temperature again, the freezer was on, current came, and everything was repaired, and then the temperature is again come back to the 8° or lower than that. But by the time 4 hours, 6 hours, or 7 hours, what the package was experienced the higher temperature, what happened to that? So definitely there will be formation of the microbes or bacteria or any other organisms which basically will not be visible in a naked eye. So there are some packs which called as intelligent packaging, which will give the indication by changing the color of the label, and it will indicate that the food is spoiled or would not to purchase the food. Like this is example where we call as intelligent packaging. So intelligent packaging are having the ability, that is a sensing devices, which are normally used by the nano inks or nanomaterials are used in the ink and all the sensors. Okay, so here if you see, there is a sensor here which is shown the dark blue inside and the gray color outside. So here if you see that on is written in the blue color, and here also if you see, the tick is given on the dark blue and there is a cross mark given on the ash color. So this level indicates basically if the level of the color of this indicator changes from blue to gray, this is spoiled, there is a cross mark that not to purchase. And if this is blue, we can here a tick mark is given. So instruction will be written in the level. Okay, so this type of packaging are also available. Normally this type of intelligent packaging devices are used in case of frozen food, or on sometimes it's a fruits and vegetables, because fruits they respire and there will be formation of ethylene oxide, and if the ethylene oxide is more, the fruits will get ripen very fast. And nowadays, if it is coming inside the box, we cannot touch and get the feeling of the fruits. So how to understand whether the fruit is spoiled or not? So if this type of sensor are connected or applied or used in this type of packaging, we can understand. So this type of packaging devices are called as a intelligent packaging, and where this nanoscience is working, and a lot of companies are there who are using this nanotechnology for designing these sensors. There is one more oxygen level indicator also. This is also called as intelligent packaging, may be used in case of chips and other things. So where if oxygen is going inside the pack more than a concentration level, so it will change the color and will indicate that oxygen concentration is more inside the pack and the product is not best as when it was manufactured. So there is a company who is called IMPAC Corporation. They are designing this type of sensors which will indicate by changing the color of the sensor in concentration of oxygen. If there is no oxygen, the color is pink. If oxygen concentration the pack inside is more and more, it changes the color from pink to purple. So that is indicates that the oxygen level is inside the pack is more, and the product get rancidity. This is one more smart packaging. We can say this is smart packaging. So what is that? This is called as a self-heating container. It is used by Nestle in Australia. So this is basically a special pack where there is a push button is there. If you see bottom, there is a push button. By pressing this button, we can get the coffee hot within 2 to 3 minutes. Okay, normally in the cold countries or even in our army, so defense services, like the people who are working in the Leh, Ladakh and all these things, our Indian armies are working. So if they want to have a hot coffee, how to get it without put fire and all these things. So there is a packaging which is giving a such facility that with pressing a button you can get this coffee or tea hot within 2 to 3 minutes. So there is basically, if you see, there is a push button is there, and inside this can there is a two chamber. Inside this smaller chamber there is a quick lime, there is a diaphragm, and then the water is there. So blue, this is a water, and then this is quick lime, and in between this there is a aluminum foil or maybe rubber diaphragm. So when you push this button, it pierces the aluminum foil or it bursts the diaphragm. Because of that, the quick lime and water will come in contact, and there will be a chemical reaction which is called as exothermic reaction. That is a calcium oxide, formation of calcium hydroxide and heat. And because of the heat, this material is aluminum. So aluminum is a very good conductor of heat. It will absorb the heat, and the inside coffee will get heated up within 2 to 3 minutes up to 70 degree centigrade. So that is basically is a example of a smart packaging. These are some examples of smart innovative designs which have been done, and this is a the pack which created in the shape of banana. Normally banana we cannot carry during transportation or traveling time because the skin is very soft. So for banana also one case has been designed, and this banana can be carried in the time of transportation. These are some levels which must be given in the labeling information as per the Food Safety Act. Like all of you might be knowing also, this is a veg logo, this is a non-veg logo, which calls that inside food will be non-vegetarian, and this indicates the food product which is not for consumption, human consumption. There are some food product which might be which are not suitable for consumption by the human being, so that will be coming as a cross. Like some example I'm giving, say the honey we are using for puja purpose, or there are some other ghee and all these things which is used only for the puja purpose, because the purification level will not be good for that, and it cannot be consumed by the human being. So these are all available in the shop which they sell the items for the puja purpose, so that cannot be consumed by the human. So there in the label they need to put a cross mark by the manufacturer, so that it will indicate it is not for human consumption. And this is the logo or the symbol which is used for any food products which is undergone the radiation, that is called radura. Radura is a symbol to be given on the package if the food products undergone radiation, okay, to indicate that this process of radiation has been taken for purification of this food. And this is for the organic products. We need to have a Joybik Bharat logo, which is designed very recently, and FSSAI mark is always there. It has to be given on the package containing the food products, because FSSAI is a mandatory regulation, and any food business operator need to follow this regulation. Okay, and this is a symbol which is eco-friendly symbol. The triangle indicates that the packaging material is recyclable, and this eco-friendly written around this is indicating that the packaging material is friendly to the environment. That is, it is a either oxo biodegradable or it is a biodegradable film or material which will not create any problem, and after a certain time it decomposes and mixed with the soil, and this symbol indicates the packaging material is recyclable. These are the various symbols used in the plastics containers or packages to indicate what is the type of the material used for packaging as per the pollution control board's norm regulation, that is the CPCB regulation. Any packaging made up of plastics has to have a symbol indicating what is the material. Like the three arrows making a triangle indicates that the packaging material is recyclable, and this number indicates what is the material used for this packaging. 1 indicates polyester, 2 is HDP, 3 PVC, 4 LDP, 5 is polypropylene, and 6 is called polystyrene, and 7 to 19 for reserve for the other plastics which are not yet been allocated in number. So this is called as a recyclable packaging material, which basically these symbols will be used by the the solid waste management department. That is a corporation or the garbage. The people who are working, they are collecting back this material from the environment, and then they has to segregate, but depending upon the symbol put on the consumer. Any plastic container, the number has to be embossed. It will be embossing on the container, not in the label. It has to be embossed, because in the waste management the label will be separated or detached from the container. So the container body, the symbol has to be mentioned by the solid waste management department. They are going to segregate and then recycle this material as per the regulation. Okay, now there are some these things which are most of all, there are something which is called as a, the packaging, what I told, that main purpose of packaging is to provide protection to the product. First is the containment, then protection. So it has to protect the product from the different hazards like climatic hazards, and also from the mechanical hazards, which is basically called as, a mechanical hazard means during the transportation and distribution. So basic hazard, first hazard, that the primary packaging might or must give the protection to the product from the climatic hazard. Climatic hazard means the hazard which are generated from the climate, like change of moisture, oxygen, light, heat, cold, all these things are there, which creates problem with the product. Any food product contain oil will get deteriorated by the oxygen. And moisture, if any food products having a low moisture content like coffee, milk powder, potato chips, tea leaves, these having a very low moisture content, 2 to 3%. So any product which contains very low moisture, they have a critical moisture content within, say, below 10%, 4 to 5%. For such product, we need to have a very good barrier material, otherwise moisture will come inside and product will get spoiled. Now there are some nanoparticles which are used in the plastic materials to increase the barrier property, that is the moisture ingress will be less, oxygen permeation will be less. So there are few materials which are used, and because of the application of this nanoscience in this material, plastic materials, what is happening, we can reduce the value of the moisture ingress, that is the WVTR, water vapor transmission rate, or called as a oxygen transmission rate, OTR. So these values can be reduced by doing application of this nanotechnology in the normally it is done with the bioplastics or the natural plastics. And light, heat, and cold also are coming from the environment, and this is also called as a climatic hazards. Now if you see in atmosphere, there are almost 21% oxygen is there. So any product which contains the oil will get spoiled by this oxygen, because in atmosphere we need oxygen, but any food product which contains oil does not require, oxygen comes, that will get oxidized and get rancidity. So we have to give a protection. So for such product, we need to have a packaging material which have a high barrier of oxygen, that is we call as a OTR value should be very low. OTR means oxygen transmission rate. Okay, and these are called as the mechanical hazards which a product undergoes during transportation and distribution, like drop, vibration, compression. When a material is loaded in the lorry, it may get dropped from the hand of the laborers, so it may get busted. Vibration also there during vibration. If it is a liquid product, there may be leakage from the closure, or due to vibration, say when the cold drinks or soft drinks is there, when we vibrate, the generation of carbon dioxide will be more and more inside the pack, and because of that there should not be any leakage to the cap and all these things. So these are all mechanical hazards which undergo during the transportation and distribution of the packaging material. And we also have to follow one that is a formula called 4R hierarchy. From the environmental point of view, whenever we design any packaging, we must follow this 4R hierarchy, which is called reduce, reuse, recycle, and recover. That means the packaging material consumption has to be reduced as minimum as possible. We have to reuse wherever possible. Like if you see the glass bottles, plastic pallets, and wooden boxes are all reused for packaging. Recycle wherever possible. If the material is not eco-friendly or biodegradable, we have to use a recyclable packaging material which will be recycled, and the end user, like I show you the plastic packages coming with the triangle and the number, which indicates that these materials are recyclable. And the packaging materials which are not recyclable, that has to be used for recovery of the energy out of that, or maybe sometime we are doing the pyrolysis process and getting some organic solvents from the packages. Like this is now the innovation which is happening in the packaging for the last couple of years. Here you can see there are some examples of the companies and the the latest innovation happening in the packaging, like Internet of Packaging, IoT technology, then biodegradable packaging materials, digital printing, packaging automation, active packaging, then you say customized packaging, recyclable packaging, edible packaging. There is another branch to edible packaging, like say ice cream cone. There is a ice cream is given in the biscuit and we eat that. So this type of packaging also there are some edible films. Then 3D printing is done for the consumer attraction and beautification. Then nanotechnology. So these are the innovations happening in the recent days. So there are a lot of things happening, like if 3% is the 3D printing done globally, nanotechnology also 3% used in the packaging, edible packaging almost 5%, then customized packaging 5%, active packaging 8%. So these are all some data which is given by the Startup Insights journal in 2022 January. Now, what is nano? I think already last couple of days are been in the session is happening in the nanotechnology. What is nano? I think everybody knows. So nano, basically, if we see the unit of measurement, so 1 meter is 1000 millimeter, and 1 millimeter is equal to 1000 micrometer, and 1 micrometer is equal to 1000 nanometer. So small, 1 millimeter is measurable. So we can have a scale in that we can see 1 millimeter. So if we divide 1 millimeter into 1000 part, we get each part is called 1
Excuse me,
micrometer.
sir.
Pardon?
I'm sorry to interrupt. Sir, within 5 minutes, you have
Yes,
another
ma'am.
5
Yes, ma'am.
minutes
I'm just
left.
finishing
Thank
up. Yes, yes, ma'am.
Yeah.
And so this so much of less particle size can give the very good barrier property, and also the surface will be very good. So with lesser quantity of it can be used in the coating industry, in the varnish industry. So by using this, the more surface area is coated or printed. As a result, we are saving the material, and the cost benefits coming. So there are a lot of specialty varnishes available, specialty coating available, like clay coating is also available, clay nanoparticles, so which increase the property of the paper and paperboard, which is used in the packaging for attractive printing or any surface properties. Even the the nano sensors are there, which is used for intelligent packaging. I give some examples where we can, I think I'll come to that, where we can see the present packaging where nanotechnology is used. I'll give some examples. Normally in packaging, there is a silver nano components are used, which is basically used in the antimicrobial coating is used as a silver nano components. So where it is after the corona, there was a people are afraid to get anything, touch anything. So that nano silver coating was given on some packaging materials, and it creates the packaging surface antimicrobial this thing. I'll give some example. The current packaging systems where we can find, there are in India also, there is a company called Novarak Innovation Private Limited, which is a startup company by IIT Mumbai. They also filed 4 patents already for the field of nanotechnology using, and they are developed some coating materials in the packaging which is used, like the medical devices packaging, medical equipment. So they are giving a spray which is coated on the surface, and it makes the surface disinfected. I'll just come. Yeah, these are the some of the nano silver based packaging containers available across the globe. You can see there is a company called Sharper Image Company USA who have developed a nano with the polypropylene. Okay, and this is used in the packaging of fruits and vegetables, and even for the breads, also cheese. So this is creating a very good barrier. So this polypropylene is inherent, giving a barrier to the moisture and also to the gases which is not come inside the pack, and as a result the product will stored for the longer duration. Then there is a Sina antibacterial food storage. It is in Vietnam. There also in the polypropylene copolymer has been developed with the nano silver, and this is removing the bad smells and prevent jumps with the growth. So these are all the different, though I am telling commercially it is not available. Even if India also, if you see commercially huge quantity of nano still under development stage, it is not been used, but it is not in direct contact with the food package, because there is a people are afraid that nanoparticles would get migrated in the food. As a result, it is not used in contact with the food product. Maybe it is in the outer surface of the packaging material, so that inner surface which is in contact with the food is not encountered, so that the migration will not happen. Because of the low particle size, it may migrate into the food. That is a leaching. So normally we check the food grade test with the chemicals, that is called NF10, which we do as per the IS 9845 Indian standard, where basically we are exposing this chemical with the food. Like if I do to this bottle, I will put this NF10 inside the bottle, keep it for 40 temperature in the oven for half an hour, and then take out and do the extraction and try to find out whether any weight gain is happening. That is, weight gain will be happening by leaching of the packaging material inside the chemical. So because of this probability of leaching, so still nano is not directly used in contact with the food products. So it is given in the coating as outer surface, or in the secondary packaging materials it is been used currently. Nano silver cutting is one of the things which is used in then we have something other also, like if you the Honeywell International USA, they are also having a nylon 6 nano clay materials, which is used for alcoholic drinks and bottles. So it will not allow the gases to permeate. So high barrier property for the gases and the other materials. Then there is oxygen scavenging also there. Normally, as I told you, the intelligent packaging or active packaging, which basically are increasing the shelf life of the food products by doing, restricting the passage of gas, or by scavenging the gases like fruits and vegetables. They are ripening very fast if ethylene gas is there. So there are some, what is called that active ingredients are there which will absorb the ethylene gas, so which will control the ripening process of the fruits and vegetables. So these type of materials are people are trying to evolve with the nanoparticles, and they are making this like oxygen scavenging, carbon dioxide emitters, and there is a, silver is used for, antimicrobial contamination protection. I think with this, I think, ma'am, I'll try to finish it here. Already I have completed, I think, one hour. Thank you very much. These are the availability of the nanomaterials which are still available in the overseas countries.
Thank you so much, sir, for your so informative talk on the packaging material. As a common people, we all use these packaging materials, but we don't know what is the composition and the function of each layer. So you have given a wide idea about this. I think our participant will get this knowledge, and they are really will be benefited out of it. So thank you once again for your time. Now we are coming to the question. Is there any question in chat box? Chinmay?
Ma'am, there are no questions right now. I would like
There
to
is
ask
no
the
question.
panelists if they have any questions.
Yeah. Sir, I have a question, sir.
Okay, please.
In your institute regarding the nano packaging, are you using the nanomaterials in which field you are actually working? That I want to know related to the nano packaging.
Ma'am, frankly speaking, till whatever the the development and design we have done, still in IIP we have not used any nanoparticle nano-based packaging material as of now.
Okay.
Commercially, it is
So,
not available even in our country. Commercially, it is not there, but there are a lot of
in
research
India,
going on.
research is going on. In India, there is no product, no packaging material in market.
Yes.
You have shown the list. The other country, they have developed something, but in India, I think the scenario is not so.
Correct, ma'am. Yeah.
But there is scope.
There
Definitely
is opportunity, ma'am. Yeah, definitely it will come. Basically, now, ma'am,
yes.
what I feel now government has given a ban on the plastics. That is a plastic waste management rule has come.
Yes.
Correct. So when they are banning this synthetic plastics, so now bioplastics will be used, and there is no limitation of thickness in the bioplastics. And by property, bioplastics does not have the barrier property by which they are not used in the food packaging. Now, to enhance the barrier property, that is barrier from moisture or barrier from oxygen, we have to use this nano. Then it will be improved in the barrier properties, and as a result, it will be used as a consumer pack or as a food packaging material. Now, the because of this rule, it will open up.
Right, sir. Sir, regarding the biodegradable packaging, what is the status in your institute? Because you are the
bioplastics, ma'am. Now there is more than biodegradable. Now people are using, oxo-biodegradable film. Basically, it will not automatically degrade. So you have to biocompostable. You can say as a biocompostable. So we have to collect it. Basically, now government is looking into the more and more, what is called that EPR. If you see the waste management rule, there is a clause has come that is called EPR, Extended Producer's Responsibility. As a converter of the packaging material, as a raw material manufacturer, or as a brand owner, that is all the three industries, their job is to, whatever the manufacturing materials they are manufacturing, packaging material, so they has to collect it back. When the consumer are using and throwing it in the atmosphere, we are throwing it in our environment. So that three industry, they has to engage the NGO under the EPR that they will collect it back. What is the clause? They have given a clause that if you manufacture, say 50 tons per annum, the plastic bottle, so you have to show to the government that you have collected again 50 tons back that material. It may not be your brand, any brand you can collect, and total accumulation will be 50 tons. Okay, so that is the government is saying that as a user or as a manufacturer, you might contribute. Your responsibility is that is, you as a producer, you have to collect it back and give it, segregate it, and then do the recycling, so that this plastic waste management problem will be overcome. Okay, so that is now has come.
The responsibility of all.
Yes, yes. As a user also, we should not throw it here and there.
Yes. if there is no any other question, then
Ma'am, Ranu ma'am
thank
wanted
you.
to ask a
Do
question.
you have any question? Yes.
Yeah, thank you, Dr. This. And in fact, I mean, you have given such a beautiful awareness about this packaging. I mean, as a consumer, we use, but we never think. Now we should actually, I was really not aware of so many layers of packaging. I think whosoever is listening has got an excellent idea about what we are using. When we are using any product, what is the role of packaging here? uh, we would definitely like to call you some other time for a more elaborate discussion. Today we have a lack of time. Now, a few things that I wanted to ask you, right? We were talking about the active packaging to prevent the staling of these food material and all. Like when it comes to the milk, are there any like the milk pouches? Is Indian government or maybe your organization trying to work around prevent the staling of milk or increasing its shelf life? Because the diverse temperature is a very big problem in India. And storing milk in every house where even the refrigerator is not there. So you talked about reducing the moisture ingression, that is definitely required, and maybe even a microbial staling is to be prevented on these milk pouches probably. So what would you like to comment on this?
Yeah, ma'am. Now, actually, what I have heard that now you might be knowing that there is a institute called CFTR in Mysore. They are working on to design a indicator, that is I called as a intelligent packaging. They are going to design an indicator which will tell whether this milk, when we buy the milk pouch from the shop, we don't know whether after boiling this it will get curd or it will be, it gets
Exactly, and that can lead to a lot of diseases as well. I mean, it can lead to
so
epidemic
CFTR
also.
Mysore, I heard that they are working to on a smart, what is called that indicator. That is an intelligent packaging indicator, which will be used by the milk industry to for enriching the knowledge of the customer, that if the color changes of the level, you can say to the shopkeeper, no, I don't want this pack, because the level of the color will change, and then it will indicate the milk is spoiled, maybe due to the the formation of the microorganisms, or by the temperature raise, it has changed the chemical property. So if we boil this, it will become the chana or whatever we call as a paneer.
Right, exactly. So thank you so very much. I thoroughly enjoyed your talk, and I'm sure same with, I mean, I was having many questions, but then every time you were speaking, you were answering my queries. So right now, all my queries got answered with your talk. Thank you so very much.
Thank you, ma'am.
Thank you, sir, for your time.
Thank you, ma'am.
We want to hear from you in future also. Thank you, sir. Thank you so much.
Thank you.
Sir, I had one question. Sir, what do you define as a single-use packaging material? Like when we are talking about these Tetra packs and all, when we are talking about multiple packagings of pineapple as well. So there we are using some kind of polymer, some kind of plastic material as a adhesive or as a extra coating layer. So, sir, will these be defined as a single-use package material or not? Because when the government says that they are banning single-use plastic, uh, these kind of plastics also, I think, come under similar category.
Yeah, I think Mr. Shukla, your question is very relevant. What is basically happening? Government has identified 12 different types of plastics, which they have marked as a SUP, single-use plastic. Though the packaging also will be single-use only. Say this small bottle, this is considered as a single-use plastic. But water bottle above 500 ml is not considered as a single use, because 500 ml and above, like 1 liter. 1 liter, say you purchase a Bisleri water and then you are not throwing the bottle, it may be carried. You may carry while traveling, you can carry water inside that. Okay, but the smaller quantities, like what is given in the aircraft, 200 ml water, nobody carries this, reuse this. So this is a single-use plastic. Almost all the packaging, like if you see the flexible packaging, we are buying the tea leaves or coffee or milk powder in a pouch. These are all single use only. But government has not put a ban on these single use packaging plastics, because still now there is no substitute. If we ban some, then what is the net alternative? Like if you see the biscuit is available with 1 rupee also. One pack, one biscuit, cream biscuit of ITC, that is a what is called dark fantasy, available. One biscuit, one packaging. Correct? So if this flexible packaging is not available, is there any other alternate? It is not available. And because of the flexible packaging, you can use the shampoo or 50 paisa pack is available. Earlier, no small pack was available. Shampoo was not sold much in our country, say 20-30 years ago, because of the no small packaging. Now this packaging has created innovation, and it increased the marketing so high, multiplied by number of times. All consumer can buy. Even you see, when you travel in the aircraft or train, they are giving a 50 paisa milk powder to make 1 cup of tea or coffee. There is no substitute other than this, which can, given this type of packaging. So government still now has not banned this packaging as a single-use packaging, but yeah, they have identified some products which are called as a single-use plastic, like a carry bag, which is used for carrying of the, the vegetables or even the meat or fish from the market, or the stick, balloon stick, earbud, which is used for, putting inside our ear, and we will just throw it. Okay, then balloon stick, then, the flexes, that in a program we are creating the backdrop. After the program, it does not have any value. We just throw it, dispose it. So this type of, then plastic tumbler, teacup made of a plastic. After you drinking, we just throw it. Correct? So these are all called single use. Even the plastic dishes, which is, served for the catering services in the roadside, or if you have a food, they are giving a plastic plate on which you eat, and just it is thrown. So these have been identified as a single-use plastic, and government wants this to be banned. Okay, so that has been, but packaging, as there is no alternate, it is not yet been banned, but government has given a timeline of another 10 years, and it has mentioned by this time, each company like converter, raw material, and all these user industry, they should put their scientists, you work out what is the alternative of that. So government is allowing again 10 years for using this. Otherwise, there is no alternate. It has to be stopped. Yes, I think I am able to answer your query.
Right, sir. Very well answered, sir. Very well. Yes, sir. Well. So, if no further questions, then I thank Dr. Bidan Das for this amazing talk, where he explained all kinds of packaging and solved the queries of the participants. And now I would like to welcome our next speaker for today's event, Dr. Aviru Kumar Basu. So Dr. Aviru Kumar Basu is currently working as a scientist / faculty at Quantum Materials Device Unit at INST Mohali, DST, Government of India. He completed his PhD from IIT Kanpur and postdoctorate from NUS Singapore. He has published several peer-reviewed publication journals, conference proceedings, and books. His research area includes MEMS and NEMS devices, gas sensors, biosensors, nanofabrication, 3D printing, nanotechnology, and 2D material-based devices. The title for his today's talk will be Design and Development of MEMS-based Sensors for Rapid Detection of Trace Analytes. Sir, I would kindly request you to restrict your talk between 45 to 15 minutes, followed by question and answers. The stage is yours. Thank you very much, sir.
Thank you very much, Chinmay, for such a nice introduction, and very good morning to everyone, to all the faculty members, students of Amity University. Is my presentation visible?
Sir, not yet.
Not yet, sir. Not. It is coming. Now it is visible, sir.
So good morning, everyone. So basically, I work on the MEMS, MEMS-based devices, and mostly I here joined recently last year as a faculty, and our motive is to develop the MEMS devices for detecting gas molecules, biomolecules at very, very low concentration by surface functions in the MEMS devices. So what is basically the MEMS? MEMS is basically, if you can see, is the combination of microfabrication, electronics, mechanical, as well as the biological portion and sensors. So this basically a combination portion, MEMS. Now, the fundamental thing, the sensor which we use in MEMS is the cantilever or the resonator. So how a cantilever works? We have so many buildings all across our country. We have, and all the buildings consists of fundamental thing. The basic portion is the cantilever beam. My role or our lab role is basically to fabricate these cantilevers in nanoscale. So what happens when we scale down these cantilever devices? When we scale down these cantilever devices, we can use it as a sensor. We have faster response, we get better sensitivity, and as well as lower energy consumption in terms of VLSI. So how we use these sensors how we use these cantilevers as a sensor? So cantilever is fixed at one end, and other end of the cantilever, as you can see, is fixed. Feel free to rotate. It can rotate in static mode or in dynamic mode. So basically, there are two modes of cantilever. Main is the static mode, and another is the dynamic mode. So what happens basically? When some gas molecules or biomolecules gets attached on the surface of these cantilevers starts vibrating or sensing those molecules as stress gets developed on the surface of the cantilever. Now, if it is in the static mode, we can detect through optical beam deflection technique. I will go into the details. If in the dynamic mode, we use other mechanisms to measure the resonating frequency, and shifting in resonating frequency occurs in the dynamic mode. As a result, we can sense the number of molecules getting attached on the cantilever surface. So this is basically the governing equation of the cantilever beam, the micro nano cantilever which we use for sensing mechanism. This is the very popular developed by Stoney, because we follow the Stoney's equation. The surface stress is there. We can measure the deflection. We put the other properties of the cantilever beam in the equation, and the material properties of the cantilever of which it is made of. And from that, we can know ultimately when the cantilever deflects, the deflection as well as the stiffness of the cantilever. So how this cantilever beams basically works? As you can see, this is from one of my previous published papers. So this is from how these biomolecules are getting attached, or gas molecules may get attached on the cantilever beam. So we functionalize this surface with different biomolecules or different nanomaterials, and the biomolecules get attached on the surface of the cantilever, and deflection of the beams basically occurs. So what happens when the deflection of the beam occurs? The laser beam which falls on the tip of the cantilever, it gets reflected and captured on a CCD photodetector device. From there, we can measure how much the deflection is occurring. In the figure B, you can see there are the other modes of deflections of the cantilever. You can see here. You can the torsional mode, the lateral mode, different modes are there. How this cantilever beam deflects. So it can rotate like this. It can rotate like this. It can rotate like this. Different way it can deflect, and according to that we can set up our optical setup or other electrical setups to measure the deflections. So the cantilevers we make, it can be of polymer or as well as of metals, but I prefer to make the polymeric cantilevers because it is much more bio-friendly and easy to make. So how do we fabricate this kind of devices? We use in the using the nanotechnology equipments. How do we fabricate it in clean room? So we use silicon wafers. We use spin coater for spin coating the thin films on the silicon wafers. We pattern it with mask aligner, and we etch it to release the device, the suspended beams, to get the cantilever kind of freestanding structure. So you can see here the different types of cantilevers we fabricated. This is first, you can see the rectangular beam cantilever. You can see the M-shaped beam cantilever beam. This is a V-shaped beam cantilever, and these are the array of cantilevers of different length and width. Most generally, you will see the rectangular beams cantilevers in the market, or in the FM also you may see the V-shaped cantilever for in the tapping mode or in the contact mode people are using. We can fabricate the other modes also. I fabricate this M-shaped cantilever, particularly it may be used in energy band harvesting. So this kind of cantilevers are new and novel. Now, how this cantilever, I use mainly the static mode setup because it gives more accuracy for sensing, and we can detect up to much more lower level of concentration of analytes with this static mode setup compared to the dynamic mode setup, because in the dynamic mode setup electrical setups are there, so erroneous results can come due to biomolecules, due to the gas molecules. But if we consider the optical beam deflection setup, here the chances of accuracy is much more and the error is much more less. So how we use measure the deflections in the nanometer of these cantilever beams? Here we use a helium neon laser. We point it on the cantilever beam. This is our reference cantilever, which is not undeflected, and we take the differential beam measurement to measure the analyte concentration, which we can detect on our cantilever beams. And you can see here, we finally record it in PC, and we process the images through MATLAB to get how much deflection has occurred after we flow a gas at different concentrations, at maybe at ppm, maybe at ppb, or the biomolecules at different concentration, at micromolar, femtomolar, nanomolar concentration, different concentration. So this is the microfluidic channel. This is the optical setup. We place the cantilever in it, and we use a motorized sewage pump to flow the gas molecules or the biomolecules. And in this small microliter reservoir, it's around 100 microliter reservoir, which we fabricated. On this, we placed our cantilever beam, and we can measure how much the deflections are occurring. So basically, this is the deflection setup. Now, you can see here at the right side, the cantilever beams. This is the M-shaped cantilever beams. Two laser beams are pointed on it. On which the deflection will occur, and another on the undeflected beam, which a very less deflection occurs due to the fluid flow. But binding does not occur here. Binding occurs here, so we take the differential deflection. And this is another on the V-shaped cantilever tip. You can see the glow of the laser. We have taken these images with simple microscope, small portable microscopes. Now, how do we fabricate this kind of cantilevers? In details, we use AutoCAD softwares for designing the mask. We use, as we said, we may use hard mask, and better if we can use the maskless technique. So we can reduce the cost and the time and the labor using the maskless lithography setup. And we functionalize the cantilevers using inkjet printers. So we fill up the inkjet printers. There is also cantilever, and there is a microfluidic channel. We fill the microfluidic channel with the specific liquid we want to surface functionalize these cantilever beams, and you can see how we functionalize this cantilever arrays, the drop by drop. And finally, this is our optical setup through which you can see there is mirror, beam splitter, all those proper optical setup is there. We can measure the optical beam deflection. And finally, this is the spot we get. Two spots you can see here, one from the reference beam and other on the cantilever beam, one from which deflection is actually occurring. So different applications of cantilevers are there, which I have used. Mainly I will be focusing today on the gas sensing portions only. So if you can see here, what I was saying, multiple detections can be done on this cantilever thing. You may do biosensing or gas sensing. For biosensing, we may do this multiple array of cantilevers are there. Multiple markers may be detected, antigen may be detected, gene fishing may be done, or we can do gas sensing also. multiple molecules may be detected if we surface functionalize this cantilever with different nanomaterials on the surface. And still, I should not say that it's a totally point of care diagnostics device. This is still a lab on chip diagnostic kind of device, but we are trying to make it a portable device, point of care diagnostic based, so that we can it should be portable. We can anywhere we can place it and detect any gas molecule or biomolecule. Now you can see here a cantilever beam of one of Busan at South Korea, world's largest cantilever roof. You can see how big it is and what's the dimension it is. It's such a big beam. And this is the nano cantilever beam which I fabricated. So this is the 200 nanometer freestanding cantilever beam we use for sensing purpose. This was I fabricated at IIT Kanpur, and now we are also started a little bit fabrication here with our own setup in our lab. So different applications are there. As I was saying, this you can see the biomolecules are detected here. This is another from Purdue University. They have detected vaccinia particles at femtogram. Now I will move on to mainly the gas sensing portion. So what happens? We can detect different gases. One of my focus was to detect chloroform, because there are many sensors available in the market, but they could not detect these volatile organic compounds at very low concentration. It was literally not possible. There are many gas sensing mechanisms are there, impedance based, simple electrodes based, which I have also done. But cantilever can give that kind of sensitivity, which I feel other sensors is not possible to give. So chloroform was previously used mostly as an anesthetic agent. Now it is no more used, but still it is used in industries, in a lot of industries, as well as in all of our laboratories. In the chemical laboratories, we use chloroform for different kind of synthesis. As a precursor, as a solvent, we use the chloroform. And so it is basically very hazardous, and it can cause different diseases in humans also. If we inhale chloroform at higher concentration, it can give harmful for our health as well as for our organs. So the sensors which were previously developed for chloroform, mostly you can see in the 500 ppm level, 23 ppm level, 100 ppm level, and some companies they are also developing like Gastane, Sensidyne, but no one could reach below that level. It was not possible for them, and even many companies could not detect this chloroform or the volatile organic compounds at room temperature. So my focus was to detect these chloroform molecules. Our focus to detect these chloroform molecules at very low concentration at room temperature with high sensitivity and specificity. So chloroform, as we know, it's a colorless gas. Some smell is there, and it's generally insoluble in water, but soluble in mostly organic solvent. As I told you, it was previously used in anesthetic. Now no more chloroform used. Fluorine gases are used, isofluorine, sulfofluorine, all those gases are used now as anesthetics, and it's still used in pesticide as a preservative for dead bodies. So, and how it affects? It affects the CNS, central nervous system. It can cause cardiovascular depression, liver necrosis, and also bladder cancer. So first, for detecting the chloroform molecules, we synthesized graphene oxide based nanocomposites. So you can see the reduced graphene oxide sheets here, and on it, I basically functionalized with carbon nanotubes, multiple carbon nanotubes, and ferric oxide nanoparticles. So these are the ferric oxide nanoparticles, the RGO sheets, reduced graphene oxide sheets, which we use for functionalizing on the cantilever. And we checked whether the composite is successful or not with different spectroscopic techniques, which different like Raman, XRD, TAME, all those techniques we used, and XRD, to know whether we can make our composite successfully. And after that, we how advantageous was to dope with CNT. We checked that also, that whether the surface area is getting increased or not, because that is one of the most important factor I consider for gas sensing. So we saw with when we dope with CNT, this RGO alpha Fe2O3, I used RGO alpha Fe2O3 for other gas sensing also, but when we dope with CNT, it showed very specificity to the chloroform molecules, and we observed that the surface area also getting increased because this is an important factor for absorbing gas molecules on the surface. Now, how this chloroform basically reacts, you can see here, when we functionalize intermediate compounds are formed, and ultimately it is getting released like this CO2H plus Cl minus after reacting when the chloroform molecules react with the nanocomposite we develop RGO MWCNT ferric oxide. So these are the deflections which we get. So what we do first, like for biomolecules, basically we first flow PBS to know just at neutral pH how it is responding. As a carrier gas, we use here air. So we use air or nitrogen for the gas sensing mechanism, and we flow air, and you can see there is very minimal deflections on the cantilever. And after that, we surface functionalized the as I showed with inject printing mechanism how we surface functionalize these cantilevers, and we compared with different composites by surface functionalize the cantilever surfaces. How is it behaving for this particular VOC? So what we observed, we could get good response recovery within 5 seconds, within 4 seconds recovery, and most important thing of this cantilever, it has a high, I also checked the mechanical properties, it has a high resilience. It means it is reusable as well as repeatable. Repeatably, it can be used in the cantilever. So now, other than this, this RGO alpha TO3, you can see I have used RGO MWCNT alpha TO3 at different doping concentration of multi-walled carbon nanotubes, and we were able to detect up to ppb concentration in our laboratory, and you can at room temperature, and you can see how fast it is. Within 2 or 3 seconds, the cantilevers can detect these molecules. We did also a selectivity study with different these composites. We also did humidity sensing with by flowing water vapor molecules, and we did selectivity study with other volatile organic compounds like acetone, ethanol, methanol, propanol, and we observed that our target gas chloroform can be detected at very higher at very low concentration, and deflections were much more with faster response as well as recovery as well as with high selectivity. So this is a comparison study of the cantilever beam with the particular chloroform. Now, as I was saying, we also use simple impedance-based sensors. We like with Keithley source meter, we make electrodes and we detect gases. So another gases we detected, that was carbon monoxide. So carbon monoxide is a very harmful gas. It's known to everyone. As you can see the images, mostly how the mining workers are getting affected due to these gases, and it is experiments from the motor vehicles. We are getting this carbon monoxide heating systems. There are a lot of sources for carbon monoxide, and carboxyhemoglobins basically gets formed, and how does it affect our body? It can be, we have studied in our biology, basic biology classes also. Now I'm not going to go into much details about it. So in this case, what I used, I saw there was one paper. They were using some ferric oxide, but not specifically alpha Fe2O3, and they were trying to sense some carbon dioxide or carbon monoxide molecules, but they didn't get so much high sensitivity or selectivity. So I thought, what happens if we incorporate this reduced graphene oxide, basically the graphene oxide sheets, with the ferric oxide nanoparticles. As you can see here, the overlapping ferric oxide nanoparticles on the reduced graphene oxide sheets in the HRTM images. Similar spectroscopy studies were done with Raman or XRD and other like FTR or other studies like FESM we do. And we synthesize by solvothermal or hydrothermal synthesis. And what we observe by doping, first our surface area got increased. That is the main parameter which I consider, as again I'm telling. And another thing is what we see when we use simple ferric oxide for sensing the carbon monoxide gas molecules, the response and recovery was 42 seconds and 37 seconds. But when we dope with the graphene oxide, the response and recovery reduced to half. You can see from 42 it's 21 seconds and recovery was on 8 seconds. And we can detect it up to 10 ppm and completely at room temperature. So this is the comparison study we have done with different by doping with reduced graphene oxide, and we also observed our sensor is very much selective to the carbon monoxide gas molecules, because we flow other gas also into the device, and we observe. So you can see here the oxygen, the hydrogen, and nitrogen, but the response of carbon monoxide is much more. It means the material is very selective to the carbon monoxide. So this is the way basically we developed our carbon monoxide sensor, which was very selective to carbon monoxide gas. And this is basically the absorption mechanisms which happens when carbon monoxide we flow at different concentrations on the surface of these nanomaterials. So this is another comparison study. You can see that people have made. They have used hydrothermal, they've used salt gel, different mechanisms for synthesizing these nanomaterials. But mostly they have used temperature. You can see how high temperature, like 400 degrees centigrade, 150 degrees centigrade, 1600 degrees centigrade. Only 1 or 2 papers we saw they are doing at RT, room temperature. But their response and recovery was quite high. You can see here the recovery was 900 seconds and our recovery was only 8 seconds. Compared to this, we can see 30 and 21. So this was very fast and very responsive sensor, I should say. Now, another thing I want to mention, though it is not relevant to our today's workshop, but as I was telling, the cantilever was can be used also in the biosensing mechanism. So at very low concentration, if we flow the analytes, like in the femtomolar, nanomolar, at very low concentrations, we also we can detect analytes at very low concentration directly from blood serum. So this is another advantage of this cantilever devices. Just 2 or 3 slides I will tell how biosensing also happens with these cantilevers. So you can see here what happens, cholesterol gets deposited on the eye when we get aged, and it affects our retina. So, and what happens, age-related macular degeneration occurs, and at very low concentrations of cholesterol, our retina gets affected and our vision gets affected very much, specifically when we are at senior citizen or after the age of 40. So the affects our retina, particularly our eye, very much. So we need to do surgical excision, all those things. But before that, we need to detect how much cholesterol is there basically in our eye. So what I did, basically, we have done, we surface functionalized these cantilevers with a very novel nanocomposite with RGO, MWCNT, and with polyol lysine. What happens basically when we functionalize with the graphene oxide sheets or with carbon nanotubes, their large surface area occurs, large surface area to volume ratio occurs, which helps us to capture the biomolecules, or we should say the gas molecules, at very low concentration. So what happens specifically in my case, the amines got attached both to the carbon nanotubes as well as to the RGO sheets. It formed kind of tree kind of structure, a 3D beam kind of structure with a hanging tree on the surface of the cantilever. We functionalized the cantilevers with cholesterol oxidase, and to be specific, we even checked with different dyes like FITC, RITC, different dyes. And when we flow the cholesterol directly through the serum by extracting blood, we centrifuge, you can use the serum, or the readily available cholesterol, you can dilute it and flow through the microfluidic channel at various concentration by diluting with phosphate buffer solutions. And we could able to detect these biomolecules up to 100 femtomolar concentration. So you can see how effective these cantilevers are as a sensor. we can use it for diversified applications, for multiple applications. You can use it for gas sensing, you can use for volatile organic compounds detection, as well as for biosensing application. I have not shown the other biosensing application. We have detected other various biomarkers for like cancer, BSA, and various plant-related biomarkers also. I have not got into the details. So here I finish. Thank you.
Thank you very much, sir, for your amazing talk. It was very enlightening to understand how one deals with trace molecules such as carbon monoxide, and also how it is useful even in the case for biology. So thank you very much, sir. I would like to ask the panelists for any questions.
Thank you, sir, for such an enlightened talk, and very nicely you have explained all the things, mechanism for this detection. Sir, I have a question.
Sure.
I work with some essential oil.
Essential?
Okay. Essential oil.
Oil.
Which are highly volatile. Which are highly volatile.
Okay.
Okay. So that type of molecule, this essential oil molecule, can it be detected by this type of sensors?
Definitely. If means does it, if it is volatile, so it forms fumes, right? So
Yes.
it evaporates and
In air.
it is already it at room temperature. It forms when it reacts with air. It forms
Yes,
fumes.
yes, it is. Yes, it is
Okay, so
volatile material.
Okay, so definitely we can detect. We can definitely detect on these cantilever beams. Means we can check it at different concentration. Maybe we can start with a little bit higher concentration, maybe at ppb,
Yes.
and slowly we can maybe mixing with as it mixing with air more and diluting it, we can detect up to low concentration.
Right. In liquid, because that oil is soluble in different type of organic solvent. So in solution form as well as in air, what is the concentration of that vapor? Because it acts as the insect repellent, that what particular concentration it repels the insect. That is my actual means idea
nice.
how you can.
Very nice to know. Very nice to know. Okay.
Yeah.
So we are using both the solution and the vapor form. Okay.
Basically, it should be in air. Concentration of this oil in air. That type of sensor are not available so far.
Okay, so when it is affecting the means insects, you are it's
Insect.
Okay. So means did you check the concentration at what concentration basically it is affecting the microorganisms? You means
So that is that type of means in air at what concentration it shows the repellency. That is not somehow in literature it is not mentioned anywhere.
Okay.
But in product it is there. In product it may be any type of lotion, cream, spray, etc. What concentration of that type of material, that is there. But in air, what is the release date at what concentration it comes in air to repel the insect, particular type of the insect, that is not properly studied so far. So if any this type of sensor can be developed, which can easily give the that concentration, it will be very much helpful.
Yeah, that will be very, I understand. That will be very much helpful for you. So it's that you can know the concentration at what concentration is basically affecting the microorganism.
Right. Thank you, sir. So we can try with this type what you have shown here. This type
Definitely. So actually, I could not. I didn't go into the other details. So there is various other things like cancer, the biomarkers which I have detected, and other gases also we can detect. So I just give a short overview. So multiple biomolecules we can detect on it, and we am thinking to use other materials also, and some 3D printing mechanism also maybe in future to fabricate this kind of devices.
Thank you so much, sir.
Thank you so much
for your nice talk. And
thank you very much, Dr.
Must be all the participants will get the idea related to this sensor development with this type of content.
Definitely, I will be happy to help anyone if they need any help. Already one student came last time, so I will be very happy.
Thank you so much, sir. Any question?
I would like to ask.
Yes.
First of all,
Dr.
thank you,
Rani,
Dr.
please.
Basu. Thank you for accepting my invitation. And thank you for having our student for internship with you.
Thank you very much, Dr. Nayak, also for inviting me to this talk.
Yeah, I mean, although we are meeting online for the first time, but
Yeah.
very soon I hope we can meet physically for further discussion of work. I would definitely like to collaborate with you in near future. So some quick questions that were coming in my mind, I was just making a note. So while you were saying that the commercial chloroform based sensors are not less than 23 ppm they can detect, and you have been working on this. So how low have you reached in this limit of detection for chloroform?
For my case, I have detected it's up to ppb level.
Okay, that's great. That's great. And what I understand, definitely a sensor needs optimization in several parameters. On your cantilever, you're trying to increase the surface area using these nanocomposites so that more and more gas or biomolecules can ingress, get absorbed, and accordingly you can increase the sensitivity. And you need a way for selectivity also. Now, my point is that I'll come to the selectivity question later. When we are talking about this nano cantilever, so you are optimizing that in terms of dimension or in terms of the material. Does the material matters, the lightweightness, or is just the dimension we are talking about?
Both the thing matters, I should say. See, more thinner the cantilever is, more sensitivities. So I have fabricated, you can see up to 200 nanometer. If people now can fabricate up to 10 nanometer, if it is possible, means up to 20 or 10 nanometer. Yeah, with polymer, I have not seen, but still previously people used to fabricate with silicon nitride, which are very common materials.
I mean, mechanically also it has to have a good tensile strength, right?
Right. Because repeatability and reusability is a very important aspect of this cantilever. So I didn't show the result here. We did nano indentation, mechanical bending test on the cantilever beams. Before you going into this biological sensing or gas sensing, what we do the mechanical testing of the cantilever. So when we do the bending test, we saw this V-shaped cantilevers had a good resilience, good means I should not say very high stiffness, medium stiffness, but good resilience. In terms of resilience, I mean when you're using a sensor, it should have a good response and recovery. It should come back to its original position.
Recovery is very important.
Yeah, exactly. If it is already bended, we can't use it for the for the further experiment. So what we observed, it was coming to its original position. If even we could see in the we can detect it with the photo detector also. The laser spot, it was coming when it's coming up. So that is one aspect. So dimension is a very important aspect, length, width, thickness, and the material, because the young modulus of the material has a great role in the sensing of this device. Secondly, the nanomaterials are very selective. The nanomaterial which you are using. So what happens is, the graphene, there has a very good surface area, or if we can use other nanomaterials which can have a better surface area and maybe for biosensing, so we can functionalize with amine or other molecules. So it definitely helps in our selectivity. And for bio, we can specifically functionalize with some antibody or specifically some enzyme, so it gets binded with the opposite one. Means the antigen with the antibody, with the cholesterol oxidase, the cholesterol, something like this. For the gas, it is the mechanism a little bit different. We have to test it with other gases. Then we can know how this material is selective to a particular views.
So when we are talking about, let's say, point of care devices and using these cantilever technology transduction method, so like I understand, like say I talk about the volatile gases, definitely they are going to get dissolved very soon. So you are not expending much of work or energy on reviving the sensor. But what happens when it comes to biosensors, suppose using the same technology of transduction? You have to do quite an extended process to reuse the entire thing, because each and every analyte to, right? So is it feasible with this cantilever?
It's feasible. What we do, we clean the cantilevers with PBS, phosphate buffer solutions, and we clean it and we reuse it.
So while cleaning, don't we, there must be vibrations in the cantilever while we're
Yeah,
cleaning.
definitely there is some movements
So,
of cantilever, definitely, yes. Mhm.
so I think it must have a restricted number of vibrations that these thin cantilevers, nano-dimensional cantilevers can sustain eventually. I mean, does it not affect in like say long term the life of these cantilevers the more we are using these extensive washing and all, because especially the nano cantilevers which you're showing in like 100 200 nanometer. I mean, each step of cleaning must be giving vibrations, and the eventually maybe we are losing the resilience in that material.
Yeah. So the thing is, I definitely. So every device has a means life. Any kind of device has a life. So cantilever also has a life. After that, definitely we can use it further after a some point of time. But while cleaning, another main parameter is the flow. At what concentration we are flowing? Any analyte or maybe it's a simple PBS solution. Maybe so at what flow rate we are flowing? Because flow rate we maintain at very low flow rate. We try to maintain a constant flow rate so that major vibrations or major deflections does not occur due to that. But still, if some little bit like vibrations, it's in the nanometer scale only. So suppose it is there a little bit here. So what we do the differential deflection. So if it is here also, it does not affect our work because some it is in nanometer, this is in nanometer. So we are already doing the differential deflection only. So it is getting binded here. We are taking the differential deflection. So this gives us basically the accuracy while detecting. So in this, it is not detecting. This cantilever it is detecting. So the differential deflection we can take.
Yeah, so it's a comparative thing that
Comparative
is
thing,
being
yes.
done, right? And one last question here. So you used hematite, this phase, typically with your carbon nano materials like RGO and MWNT and all. So I know hematite is good for other type of sensors also, like say nitrogen oxide based sensors also. So how do you, I mean, validate the specificity for only chloroform and only carbon monoxide using this hematite? Is there
The thing
any other functionalization being done on this composite to ensure the specificity of CO only and not for NO2 or NO?
somehow the graphene oxide has helped this composite. And what I observed, the iron at Fe2 plus or the Fe3 means that state, they are shown selectivity to the carbon monoxide much more compared to the other gases, because the other reported, I know there is some other reported papers are also
There
there.
are some reports on nitrogen oxide based gases also, or
Right.
using the same, this hematite material, whatever. I mean, but not maybe the same composite, what you have mentioned.
Maybe I think another thing, the morphology of the materials may affect somehow the how when we are synthesizing these nano materials or this nano composite, the morphology, the structure, because different paper reports different kind of morphology, different kind of structure, different kind of crystal orientations. So somehow I feel those aspects also affect somehow while sensing and for becoming the slick.
Thank you so much. And thanks a ton for accepting my invitation. It was an excellent talk, and I would definitely like to discuss more with this cantilever technology to have a collaborative work with you. Thanks.
Thank you very much. Thank you. Thanks to all of you. Definitely, I will like to collaborate with all of you.
Thank you, sir. Thank
Chinmay,
you.
over to you.
Okay, so if there are no more further questions, I would like to thank Dr. Aviru Kumar Basu sir for his excellent talk on cantilevers. And now I would like to welcome our next speaker for the event, Dr. Sumant Upadhyay. So Dr. Sumant Upadhyay is currently working as Assistant Professor at Amity Institute of Nanotechnology, Amity University. He has completed his PhD from Dayal Bagh Educational Institute and JNCSR and done his postdoc from Nanocat University of Malaya, Malaysia. He has been awarded INSA Visiting Scientist Award by Indian National Science Academy Young Scientist Award by SERB DST, and Senior Research Fellowship by CSIR, New Delhi, India. His research interests include materials for energy conversion, nanostructured materials, electrochemical energy conversion, and ab initio methods based on DFT. He has published in several peer-reviewed publications and journals. His titles for today's talk will be Nanoscale Metal Oxides, 2D Metal Heterojunctions for Photoelectrochemicals Water Splitting, a DFT study. So, sir, the stage is yours. Thank you very much. Please try to restrict your talk to 45 to 50 minutes.
Okay, thanks a lot, Chinmay, for the introduction. Let me share my screen. Am I audible and visible?
Yes, sir, you are
Yes,
audible
sir,
and
you
visible.
are.
My slides are visible or not?
Yes, sir. Please convert it to slideshow. Yes, sir, you're good to go.
Okay, so first of all, I'm thankful to the organizers, Dr. Ranu Nayak, Dr. Jeevan Mittal, and Dr. Nidhi Chauhan, and our director, Professor Rupi Sina. So the title of my today's talk is Nanoscale Metal Oxides 2D Heterostructures for Photoelectrochemical Water Splitting. So I will mainly cover the theoretical aspect in some density functional theory. So as you can see from this slide, the fossil fuels, which means most of the world's energy demand today, are being depleted very fast. And also their conversion process causes global challenges or global problems such as greenhouse effect, ozone layer depletion, and acid rain, and which are causing great danger to our environment and eventually on the life on our planet. Right. So, what is the solution? The solution is we need a clean, green, and alternate source of energy. Right? So, by replacing the existing fossil fuel system by hydrogen energy system, right, which in the second day's talk by Professor Rohit Srivastava also he suggested, he presented in his slides presentation about Government of India roadmap for 2030 for green hydrogen energy transitions. So why hydrogen? Hydrogen, as I said, is a clean energy fuel or energy carrier, and it can be stored in a liquid, compressed gas, and in the form of hydrides. And the hydrogen, if you can see from this figure, the carbon contents upon its burning or using in an internal combustion engine or in a fuel cell, the byproducts is only water and heat, right? So there is no carbon content present for its use. And the energy per unit with respect to other commonly used fuels is quite high in case of hydrogen. Is 120 millijoules per kilogram. Right. So, is my slides visible, Chinmay?
Yes, sir, you are visible, audible.
So, what are the possible ways for hydrogen production? See, photovoltaic, photoelectrochemical. So, what Government of India and others they are putting their efforts in this process. Solar thermal, wind, tidal, geothermal, hydrothermal, and biological. Right? So most of these production methods has their own disadvantages, as it was briefly explained by Professor Srivastava in his talk. So I'm not going into touch. So why this photoelectrochemical way? So photoelectrochemical way is, as you can say, is a step ahead of photovoltaic assisted splitting of water, because photovoltaic, photo PVPC, I'm using the shorter terms for photoelectrochemical as PEC, so do not get confused with that. So photoelectrochemical way is most promising because it is happening in a single step process as compared to PVPEC, because it requires a two-step process. So of course that efficiency will be lower in that PVPEC system rather than in photoelectrochemicals way. And of course, you need photovoltaic panels for that, and of course you need to collect that energy in the form of battery. So again, it is a part of research. So this PEC way is quite effective, and I would say it is a step ahead of photovoltaic assisted spreading of water. So yeah. So what is photoelectrochemical water splitting? So there are basically 4 major steps. So first one is the generation of electronic charges, meaning electron hole pairs subjected to solar radiation, yielding electron hole pairs. Right. The second step consists in oxidation of water at the surface of your photoanode or photocathode, and the third step is the production of or that oxidation which is happening, sorry, that transfer of that electron by way respectively from your photo electrode towards the photocathode. And the last step is consisting of the reduction of those H positive ion with the release of hydrogen molecules. Right? So you can see the thermodynamics for this particular reaction. So this is an uphill reaction because you require around 237 kilojoule per mole of energy to drive this reaction. Right. So PEC, this photoelectrochemical implementations of light-driven water splitting actually utilizes either one or more photoactive semiconductor electrodes to convert photon energy. Right? So I'll mainly discuss on the semiconductor electrodes using simulation or theoretical studies that how we can identify, how we can choose a particular system for the efficiency to improve the efficiency of this process. Right. Yeah. So what should be the requirements and trade-off for a semiconducting photoelectrode material, right? So it should be, it should absorb in visible light region, or there should be a good light absorption by that particular system. It should be highly chemical or high stability in the dark conditions and under illumination conditions when you are immersing that electrode in the electrolyte solution. The third point is quite important because that is why we are capturing using DFT to actually understand the processes which are essentially required for this PEC process. So that band edge positions that should spread with the water reduction and oxidation potentials. So, yeah. So the next step is the efficient charge transport in semiconductor. Of course, that charge transport, which I showed you in the animated slide, the production of electron hole pairs. So there should be efficient charge transfer so that there may not be any recombination happens because
Dr. Sumant, Dr. Sumant, are you able to hear? Dr. Sumant?
Disconnected from the meeting.
Chinmay, will you please call Dr. Sumant? Quickly
Yes,
call
ma'am,
him.
sure.
We have our next speaker also waiting. Quickly call him.
Yes, ma'am. I had a talk with sir. He'll be joining in just a minute. His Wi-Fi got disconnected.
Am I audible, Chinmay?
Yes, sir. You're audible. And
Sorry
we missed
about
it the
that.
last one.
I quickly finish. Because I've been asked to quickly finish the talk. Yeah. So I'll go quickly. However, there is no semiconductor is known to satisfy all these requirements simultaneously. So why nanostructured electrodes? And as I said, nanostructuring and nanomaterials can be used to address some of the intrinsic materials limitations and trade-offs those are mentioned above. So nano enhance in solar absorption, which was the first point, and it can greatly enhances overall charge transfer kinetics at the electrolyte interface. So these are the challenges which are already covered in the previous sessions. Conversion efficiency for this process should be 10% and so on. So I'm not going into the detail. Yeah. So what are the limitations of these studies, right? Why we are saying we should discuss with the DFT simulations of critical insight is important. So those hit and trial experimental like heterojunctions, doping, in order to find out that particular semiconductor systems, those are time consuming, energy intensive and expensive, right? Meaning expensive, wastage of chemicals. So first principles, DFT studies, those are quite helpful in screening the optimal dopant and heterogeneous semiconductor system. Our main aim of this research is to obtain trends and understanding with the use of DFT and verifying those theoretical results with the experimental results. So that to and fro feedback between theory and experiments will finally decide the systematic performance of the material which is being used in PEC water splitting applications. So the aspect is you can simulate a material under ideal conditions, but with perfect control at the atomistic level or nano level that can help in developing thumb rules in guiding the design and design of your semiconductor material systems, which is indirectly saving you time. And these calculations, these are quite comparatively cost effective as compared to experiments. And while the band gaps in our calculations are, which is the problem of DFT, however, the change in the band gaps and other electronic properties with the by using dopants and other heterojunctions, those are quite light. So we already have assessed the feasibility of this approach, and you have to find out the absolute band gaps. You have to use some other approximations, which ultimately requires huge lot of computational time efforts. Yeah. So motivation is Walter Cohen, who was awarded with Nobel Prize in 1998 for the development of density functional theory. And the ultimate goal is we are finding the solution. So you can say in a layman language that this is the advancement of the Schrodinger equation. We are actually solving the Schrodinger equation when it comes to more number of electrons and atoms. So that interaction so corresponds to many body problem. So that many body problem can be solved by help of some other approximations like Von Oppenheimer approximations and so on. But it did not solve our problem. So here comes the density function theory. So basically, the total energy, which is a functional of electron density, right? So it is the reason we call this theory as a density function theory. So I'm not going into the deep details for that. So basically, this Z and R, those are atomic number and position. So you are just dealing with the uh, atoms, identity of atoms, and the chemical structure. But there is no other input required for these calculations. So it is the reason we call it as ab initio calculation. You are starting with the scratch, atoms, molecules, ions, and so on, and which does not. And these are first principles because which does not require any experimental input, right? You are just using the basic laws of physics for that, right? So basically, our one electron problem in effective potential is shortened by this density function 3b. Rather, we are calculating for 3n variables. So of course, your computation cost will scales up as a function of n raised to power 3, and is being your system size. So in a layman or in a brief, first principles is pseudo potential based DFT helps in quantum mechanical analysis of electronic motions like phonons and all, and obtain total energy as a function of, as I said, atomic numbers and position. So we require no experimental input. So minimization of energy with respect to R gives you the structure, and second derivative gives you the linear compliances and other properties associated. So we have used Quantum Espresso, which is open source software for these calculations. Yeah, so we come to quickly for this heterojunction structure. First, the semiconductor heterojunction. So this is basically a barium titanated cuprous oxide system. So we have calculated, or we have modeled this supercell by taking this by having 00110, and on top of that, on the top of barium titanate, which is in the c-axis 001 plane. So this atomic arrangement leads to polar, right? You have a polarity in this system. So along the longitudinal c-axis. So it is the reason we have used this thick layer of vacuum to minimize the basically the effect of polarity and periodic images associated with the supercell. So these are the results. Basically, the how much is the shift in the VBO and CBO. Basically, as I said, the third point, the band edges must straddle with the water reduction and oxidation potential. So we have successfully achieved both theoretically and experimentally using that selection of that particular this barium titanate system. So that band offset calculations actually favors our charge carrier separation, right, which is very important in the PEC studies, and which helps in results in the improvement of photoelectrochemical activity. So our theoretical data for that systematic performance agrees well with the experimental results. So the second system is cuprous oxide and strontium titanate, because the problem associated with cuprous oxide is high rate of recombinations and stability, right? So in order to capture more photocurrent density, because it is a very fantastic material, fantastic photocatalyst material. So we have used heterojunction with the strontium titanate, and the the theoretical results, as you can see, uh, 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 is because of the improved charge transfer at the interface, right? So which helps in order to utilize this semiconductor for like a 2.52 milliampere at a very low bias values. So I quickly move to the system third, which is cerium oxide and cuprous oxide. Again, that cerium oxide is a wide band gap semiconductor. So in order to achieve good visible, right, a complete absorption of pseudo spectrum, we have used this wide band gap semiconductor, which is cerium oxide and cuprous oxide. So as you can see, the in this junction, right, so that electron and hole effective mass, right, so that indicated the mobility of your electrons is higher in cuprous oxide, while mobility was higher in cerium oxide. So that oxidation reduction which is happening in your system will be faster. The charge transport properties, charge transport in semiconductor, which was our requirements. So that agrees well with our experimental and theoretical results. So this is a silver dope cuprous oxide we have used. So basically, the interaction of copper oxygen copper network was quite higher in cuprous oxide which resists its use in photocatalytic applications. So by introducing silver in the lattice, so we have actually break down that oxygen copper oxygen network. So as you can see in this band structure, this oxygen appearance the valence band, so which actually helps in improving the charge gradients or that shuttling or electron transporting the charge gradients. So that reduces the corrosion and as well as the improved photocatalytic or photoelectrochemical efficiency. So as I said, in the silver dope, we also have tried with iron dope and cuprous oxide. So again, that reduction in band gap was achieved because of the iron 3D. As you can see, it is appearing on the Fermi energy level and also improves the conduction, right, which was quite lower in bulk or in the pristine cuprous oxide system. So this is the 2D, 3D, as I said, metal oxide and two-dimensional system junction study. So this A is your bismuth vanadate. Bismuth vanadate is a fantastic material, but it is having a drawback of charge recombination. So by introducing a 2D system, so we have checked or we have identified using DFT that this can actually help in transport of charge carriers very quickly, right? So we have not used MOS to be moved down to one additional orbital by taking MOSE, not sulfur, selenium we have taken. Yeah. So let me quickly share the density of states. As you can see, the partial density of states, so which tells you the contribution by each of the orbitals.
There is further a problem, network problem, I think.
I think some internet issues there.
Chinmay, would you ask?
This one, yeah, it's that.
Or else we can move on to the next
Am I audible,
one.
Chinmay? Sorry.
Yes, sir, you're right.
You are audible.
Yeah, so I'll quickly show you. These are the contributions of different orbitals in this heterojunction system. So why these results are important? Yeah. So basically, the work function we have calculated, right? So for individual systems, slab, bismuth vanadate, and MOS2, MOSE2, and the heterojunction. So obviously, you can see the work function was quite lower in case of heterojunction, so which allows that electron shuttling quickly, right? Which requires minimum energy, and also the charge is getting transferred from MOSE2 to bismuth vanadate quickly. So that problem of recombination, which was happening in BiBO4, reduces much down, and which results in higher photocatalytic activity.
Excuse me, sir.
Yeah.
Just try to wrap up
Yeah.
within
I'm just
few
wrapping
minutes.
it
Yeah,
up.
yeah.
Just in a few minutes. Yeah.
Yes.
So this is as a paucity of time, so I quickly have reduced the slides.
Yes.
So this
Yes,
is
sir.
the recent one, which is nitrogen to PiO2. So as you can see, the reduction in the band gap in anatase phase upon addition of nitrogen in the system, and also improves the balance band because of that OP oxygen 2p states. So this helps in the higher activity upon introduction of nitrogen in this TiO2 system, and our DFT and Curie results complemented each other. So these are some of the aspects, potential applications. So way forward is we are working on electrode metal oxide interfaces and their interactions. We are also trying to capture oxygen vacancies and effects on the gap states, heterojunctions, advanced heterojunctions with the 2D systems and others. like to acknowledge CRB DST for funding, Professor P. Sinasan, Director of the Institute, Vishwakmane and others. Help. Thank you.
Thank you very much, sir. That was a wonderful talk on using the insights of DFT for theoretical understanding and predicting the material properties. So now we move on to our next talk for today by Dr. Neetu Singh. So Dr. Neetu Singh obtained her bachelor's and master's degree from the University of Mumbai, after which she moved to USA to perform doctoral work in chemistry with Professor Andrew Lyon at Georgia Institute of Technology, Atlanta. At Georgia Tech, she worked on developing novel synthetic routes towards the design of multifunctional hydrogel nanoparticles. Following her PhD, she moved to Cambridge, MA, to pursue her postdoctoral studies at the Harvard MIT Division of Health Sciences and Technology with Professor Sangeeta Bhatia. The Bhatia laboratory, she had focused her research efforts for developing of nanomaterials for achieving and investigating RNAi therapy. She is also the recipient of the Innovative Young Biotechnologist Award 2013, NASI Scopus Young Scientist Award 2019, and Janki Amal National Women Bioscientist Award 2020-2021. She is currently the Associate Professor at Center for Biomedical Engineering, IIT Delhi. The topic for her talk today is engineering new materials for drug delivery, a chemist's perspective. So, ma'am, I request you to please restrict your talk to 45 minutes, followed by 10 minutes of question and answers.
Sure. Thank you for the introduction. I'll start sharing my slide now. I think it's asking me, you have to stop sharing your slide, looks like first. Can you all see my slide?
Yes, your slide is visible.
Yes, you are visible. Slides are visible now.
Yeah, let me just all right. So first of all, I would like to thank Dr. Bhattacharya and Dr. Chauhan for giving me this opportunity to speak to you all. And the topic that I've chosen today is one of the areas that we're working on in IIT Delhi. And before I get into, wait a minute, yeah. Before I get into the details of my talk today, I would like to tell you what is the motivation for our work at IIT Delhi. So I think this is a common problem that we all are facing, which is giving better healthcare to humanity. So what we're doing is we are interested in either developing strategies where we can diagnose diseases, which we call as early detection and prognostics, or in case there is a disease already and we are not aware of how to diagnose it at an early stage, let's say the person gets the disease and the organs fail, we would like to come up with strategies for organ regeneration or organ development so that we can have synthetic organs or artificial organs and then replace them with the natural ones. So that's the overall goal of our work that we do at IIT Delhi. And we are using nano as a tool to actually address these challenges, which is, as I mentioned, the diagnosis and the therapies. Why nano now? I'm sure I don't need to tell this to this audience because this is a nanomedicine school and we are trying to, I think we've heard many talks about nano. So nano, just to quickly give you in one line, nano, I believe, is in the right scale. So for example, if you want to analyze something really small, maybe an ant in the, in your soil or somewhere, you're not going to use a crane, right? That's the kind of analogy we have when we use micro scale tools, when we are trying to look at how proteins fold. Because remember, all these proteins and other structures all these biological structures, the largest that we will have is probably in nanoscale, right? So all these single units, of course, they range from molecular level, they will go from angstroms, and the largest when you have aggregates of a lot of proteins and larger proteins or larger molecules that will go into the nano regime. So with all the tools that are available, like the microscopy tools or any other tools that we have in that we've been using earlier, the scale is not right. You're using a crane to really look at really small features in your regular day-to-day life, right? So nano will be in the same scale, so you'll be able to understand all the processes better. You can perturb the processes, you can maybe interfere, you can also just silently be there and keep observing. So those are the sensors, materials, right? So that is the whole point. Also, if you consider, so this is how you can interface with biology and what advantages it brings, right? When it comes to the nano material itself, we have seen that all the material that we use, for example, metallic metals, or gold metal or silver metal, when you bring it in the nano regime, you start seeing some excellent properties which are not there in the bulk material. For example, they can fluoresce, they can have amazing surface properties, you can surface functionalize them, and so on. So these are some advantages, not only from the materials perspective, but also from a biological perspective, that encourages us to use nano. So we've been using nanotechnology and knowledge of nano materials to develop, to monitor diseases, to engineer organs, and also to develop new delivery vehicles. Today's talk, I'll be focusing on the new delivery vehicles. Now, just to quickly tell you about how is the field of nanomedicine growing. I mean, what is the traditional approach, in nanomedicine? And we call this approach as a bottom-up approach. What happens is you design a system. You have a nanoparticle system that you typically design based on literature or based on your own creative ideas. And what you do is, once you design, so these are the kind of nanoparticles you would design, like liposome and a quantum dot, a gold nanoshell, mesoporous particles, nanotubes, dendrimers, magnetic particles. I mean, the list is a long list, and we have a lot of literature available on these topics, right? Of course, you can modify them with your creativity. You can put polyethylene glycol, you can have therapeutic drugs, you can have a core shell structure, all complicated structures that you could create. You basically create these, this entire type of nanoparticles. And then what you do is you make them multifunctional, because you become a little ambitious. And once you do that, you start looking at its applications. Unfortunately, this approach has not resulted in any, any clinically translatable nanoparticle. It's very, very few materials. For example, maybe the liposomes are clinically translatable, the gold nanoparticles are, but not much. Not much has happened with new materials getting into the clinic, right? So what is the problem? The problem is, so the problem is that, I'll tell you what we do not understand the biology. The problem is, whenever we try to translate, it fails. Whatever we have seen in vitro actually fails in vivo. So what happens is, and the reason for that is, remember, the biology is not very well understood. If you do not understand the biology at the right scale, these nanoparticles are going to behave in a way which is very different from what you thought, right? So how do we understand that? What do we do? So needs to be a change in approach. There needs to be a change in this bottom-up approach. There needs to be a top-down approach. And what is that top-down approach? The approach is, you first understand the biological interactions of the material. So first understand, how is this material going to interact with the biological system? How is it going to interact with the cells? How is it going to interact with the surface membrane? How is it going to interact with the ECM or the blood component? Everything. You start from what your application is and where the nanoparticle can end up. You understand all the processes on the way, and then you come up with your solution, right? So what it means is that you would need insight on cellular interactions, and that is something which is missing in the field. Nobody focuses. We've been creating so many new materials. We've been obsessed with new materials, but we've not taken, let's say, the gold nanoparticle, which has been there for ages, right? I mean, maybe 2 decades now. We have not taken the gold nanoparticle and understood exactly how is the interaction of this gold nanoparticle with the biological entities. We do not understand if we change the shape, the size, the dimensions. There was some work done, but again, not much is there. I mean, it's not compiled as well. So we do not understand the extracellular interactions, the intracellular interaction. What we proposed when we started the lab was that you should first focus on this, then you should design your material and characterize, and then you bring it back into the system. You start looking at whether these interactions are happening the way you want or not, and then do iterations here, and then come up with a system which can be used for an application in drug delivery or theranostic or whatever. Now, this of course should be the timeline for developing nanomedicine. However, we're not doing it that way because, again, you can imagine that this is going to increase the time it takes to take materials to the clinic, right? So that's the reason why people have not been following this process. I just wanted to give you a summary of what is available. I mean, it's the summary. The slide looks really filled, and it's very complicated. And actually, the field is exactly like that. We have a lot of material which is available. For example, different shapes like cubes, plates, stars, spheres, ellipse, rods, whatever, name it, and it's there. We have different functionalizations like positive charge, different groups like carboxyl, thiols. You modify it with carbohydrates, with nucleotides. You put it from 1 nanometer to like 100 nanometers to like micron, even 200, 300, 500 nanometers. You have hybrid particles, you have completely polymeric particles, you have liposomes, and so on. I mean, this is a long list, and with each material, there are different shapes, sizes, structures, and characteristics that you can have, right? So it's a huge amount of work. Where does this toxicity now, I just mentioned to you that nano actually allows you to be in the right scale, right? And it can interfere with the biological processes. What it also means is that it can cause toxicity because it's in the right scale, right? So it can, so if I start looking at the crane, probably won't kill the ant. But if I start looking at really tiny needles and start picking, maybe I'll be able to kill the ant, right? So that's the kind of concept we're talking about. So if you have a really small particle, let's say a 5 nanometer particle, it can interfere with the protein folding processes. It can just stay there and not let the protein fold. And that could cause toxicity in your host, right? So there was a lot of confusion about what should be the ideal size for taking these materials into, developing nanomedicine out of it. So for example, developing a good drug delivery vehicle or a good imaging, modality. What should be the size? Is 5 nanometer too small because it can interfere with proteins? Then should it be 10 to 30 nanometers? Or should it be greater than 40 nanometers because then it will be bigger? However, once it is bigger, it can actually interfere with the uptake mechanisms. It cannot enter the cells, right? So then it won't cause any effects. So these were some confusions, and it's still there. We do not know it exactly. What should be the shape? For example, should it be spherical? Should it be rod-like? These kind of anisotropic structures have been shown. I apologize, there is a plane going, so you'll keep this periodic noise coming. These anisotropic structures actually will have the rod shapes will actually cause toxicity because they can penetrate through. However, if you have a spherical ones, they do not have those kind of physical rupture of the cell membrane. They can still be toxic because the uptake is very high. If the uptake is high, you have higher concentration. So it's not decided which is the right shape, and it depends on your application. Purity of the material, we are talking about metallic particles, or we're talking about inorganic, sometimes inorganic non-metallic ceramics particles as well. We get talking about quantum dots, which are cadmium based, and they can have these metal leach out, which can actually cause a lot of problems. Because we have a lot of metal in our body as well, and it can also be act as a chelating agents. There would be a lot of complications that would come out of it, right? So purity of the material is also a key, which can result into toxicity. Nanoparticle stability, for example, how stable is the material? It starts to degrade. The moment it starts to degrade, for example, polymeric particle, PLA, the PLA starts to degrade, and what happens is that you have lactic acid, which reduces the pH in the local region, and that causes inflammation. So that is a challenge. Of course, the surface charge also is very important. For example, if you have an extremely positively charged material, the cell membrane is negatively charged, it can interact really well, and it can rupture the entire membrane. So these are some considerations. What happens when it goes in vivo? So let's say I have tried to kind of come up with some happy medium that I know maybe around 30, 40 nanometers is my size, maybe a spherical particle and things like that, maybe a polymeric particle that does not degrade. So these would be solutions. What happens once you put them in vivo? Once you put them in vivo, its pharmacokinetics becomes very important. Its absorption, its distribution, its metabolism and excretion becomes very important. How does it affect, to various organs? So organ toxicity is evaluated. Hematological toxicity, which is, how does it interact with blood? Because blood is a lipid bilayer. How does it interact? That becomes very important. The immune response becomes very important. And once it enters, does it cause any aberrations in the genetic profile? So genotoxicity is very important. So this is overall when it is in circulation in vivo. Once it enters the cell or even in vitro, what happens is these nanoparticles are very catalytic. They have catalytic surfaces, so they can create more ROS. So they can have oxidative stress. They can enter and they can cause problems with the lysosomes, because remember, the lysosomes are known to detect foreign. There are toll-like receptors which can detect foreign objects, and our nanoparticles are foreign objects. The moment you have that, the TLR becomes active. And what it does is it then activates other further processes for cell death and apoptosis and other things, right? So this is also what happens, how you see the manifestation of this toxicity would be, cell death and things like that. So what the key aspects, so if I have to address a toxicity or make a better material, what do I need to address? Of course, as I mentioned to you earlier, just summarizing all the things that we've learned by now, is that we need to look at its interaction with the biological system. Once you start looking at the interaction, we need processes by which you can control the three key features. One is the protein corona formation. What is protein corona? I'll talk about it in a little bit. Second, we should be able to control its intracellular interactions. Intracellular when it enters the cell, right? So that we can modulate our responses. Third, we should be able to control ROS generation. And these are the three things that we've tried to address in our lab to develop better therapeutic modalities. So this is corona formation. What happens is that the moment you have a nanoparticle with, say, a certain charge, specific ligand, functional group, and a polymer, it enters the in vivo system by intravenous injections. And what you have in your blood is a lot of proteins. These proteins actually get absorbed on the surface of your nanoparticle. This is called as, the protein corona formation. And, of course, there's a lot of studies done which talks about how the most abundant protein will be absorbed first, followed by the one which has stronger affinity, right? So this is called as the Roman effect. Basically, what it allows us to do is that it allows it to escape immunity. So once you have the protein corona formation, it will basically, sorry, not this. What will happen is that the protein corona formation will activate the immune system. And what will happen is the macrophages will come and clear up this nanoparticle. And the nanoparticle will not be able to enter or circulate in the blood for a long time. If it doesn't circulate in the blood for a long time, it won't get a chance to reach to the target site, right? So the circulation of this material is going to be very short because the system is going to clear it up, right? So for doing that, what people have done is they have worked with different materials. They have changed the surface, they have changed the size, charge, and shape to reduce protein corona formation. They've also worked with different compositions, and different strategies have been used to avoid this proton corona formation. One of the strategies that has been very successful is basically they're saying that, okay, the most abundant protein is albumin. Let's just coat the nanoparticle with albumin, or maybe a polymer which does not allow, maybe a very hydrophilic polymer which does not allow proteins to stick, which is polyethylene glycol, right? So these two have been the most successful strategies till now for avoiding protein corona formation. What it does is, if you add albumin, it will allow you to escape from immunity, which means that the macrophages will not clear, so it will circulate for a longer time. It will allow you to improve the targeting and specificity, so it can actually go to the region, targeted region. And however, what it does is it masks your surface. You will not be able to put any specific charge that you wanted to put. You will not be able to put the functional group, and you will basically lose out all the synthetic handles that you added on your material, right? So this is not a very good strategy. So today, if you want to develop a new drug delivery vehicle, still the challenge is to reduce the protein corona formation so that we can have enhanced circulation time. And now that you're doing it, the drugs that you would like to deliver would be a hydrophobic drug, because remember, most of the drugs that organic chemists make are hydrophobic. So a hydrophilic version of it is less potent. So whatever drugs we are using, there are more potent version of it, but then there is no way you can put it in your body because it will aggregate and not get incorporated in the host. It will not be absorbed by the host, right? So that is why you require this delivery vehicle. Now, solution for this, and I'm not the first one talking about it. This is the challenge for past maybe 20, 30 years, right? So the solution for this is nanoparticles and liposomes. And why use nanoparticle again? You can reduce the protein corona formation because you can make different polymers and other things, and you can have coatings on the surface. Nanoparticle also allows you to do passive targeting, so you don't really need a targeting ligand. What happens is that small molecules can reach everywhere because they're really small, and that's why you have more toxicity. However, your nanoparticles, which are slightly larger in size than small molecules, are reach there only to regions which are, the blood vessels are perforated. So if there is a gap, it will be, the nanoparticles will be able to cross that gap, and that is called as the EPR effect. So you can use this passive targeting. Of course, you can use active targeting by making targeted nanoparticles. So you could use passive targeting as well, because near the cancer, you have more EPR effect. And when you deliver your nanoparticle, it will enter the tumor region more compared to your small molecules. You can, of course, increase this long circulation time. You can increase the circulation time of these small molecules because remember, we can have protein corona on the surface itself, like albumin and all that, right? So, so this is basically, and lot of clinical drugs have used this strategy. For example, I'm going to skip this one. For example, liposomal doxorubicin is in Doxil. It's the trade name is Doxil, and it is being used in clinic. It's one of the most commonly used chemotherapeutic. Then there is this albumin-bound paclitaxel. It's just simply the paclitaxel connected to albumin, and that has been shown to be very effective in patients. So, now if I'm talking about liposomes, which is already used, or Doxil, which is already used, and paclitaxel and all that, then we have a solution. Liposomes seems like is a solution, right? Let me tell you quickly what are the challenges with liposomes. The challenges with liposomes is that they have something called as the polyethylene glycol. The polyethylene glycol is a very hydrophilic polymer. Remember, I told you that you want to reduce protein corona formation. So one of the strategy is that you keep a polymer which does not allow the proteins to stick, and proteins are hydrophobic. Some proteins are hydrophobic. So if you keep a very hydrophilic polymer, they don't come and stick to the surface, okay? So polyethylene glycol is one of those polymers, and it is very commonly used in many drug delivery vehicles to reduce protein corona formation. However, because of this polyethylene glycol formation presence, there is something called as the CARPA effect, or the complement activation related pseudo allergy, which is hypersensitivity reaction induced within minutes. So I don't know if you read in your newspapers about the vaccine related allergies, and most of the vaccine platforms, especially the mRNA ones with Pfizer and Biocon, had polyethylene glycol on their surfaces. They were liposomal structures, right? They had polyethylene glycol, and Moderna, in fact, gave a news article, they gave a clarification that don't worry, this is just because of polyethylene glycol and it has been observed, nothing to worry about, it is not a side effect of your mRNA vaccine that we have, right? So this is kind of the state right now. We have strategies, however, they are not foolproof and they're not the best ones that you want. We have some compromises that we are making. So with this knowledge, where we started looking at, when we started this journey in drug delivery in 2014 at IIT Delhi, we started asking this question. Nature, we've heard, as a researcher, we've heard that nature has solution to everything. Nature has been doing it, and most of the research that we try to do, especially in biomedical and healthcare, we're trying to mimic nature, right? So we started looking at the same question. We started asking, well, let's see how nature does it. How does nature deliver drugs or deliver molecules in the body? And we found that, of course, there are many proteins that are known to deliver these things. However, one of the most common delivery vehicle, which is always in circulation, is RBCs. RBCs actually deliver heme, through heme, oxygen to every region, right? And these RBCs, if you look at them, they're just simple structures. These are simple sack of lipid bag. And this is the surface view. You can see that they're about 7.5 micron in size and 2 micron thick. So they're like disc structures, okay? The disc structures allows them to circulate in the system longer and better. That maintains the dynamics and kinetics of the whole thing. What the lipid bilayer actually gives them the cellular entity, and it doesn't have many organelles. It doesn't have anything. It has a little bit of nucleotides and some proteins which are present, which is very easy to remove, right? So you basically, and they can, now the question that we asked is, can we take this RBCs and then use it for delivering our drugs? Because if you look at the, I'm just going to show you quickly what these RBCs look like. They have, these lipid bilayer, which is very similar to liposomes, right? I mean, if you look at the liposome structure, I'm going to go back to my slide where I had exposed to you this liposome. This is the liposome. This has a lipid bilayer, right? It has a aqueous core, it has a hydrophobic layer, the lipid bilayer where you can put in hydrophobic drugs. And to me, if you look at this structure, it looks exactly the same. Just that nature uses all these water-soluble things to put it in the core of RBCs. So you can remove it, and then you can use the same. By the way, the lipids that are present in RBCs are also similar to the lipids that we use in liposome development, okay? So they're exactly the same. Now we started looking at, okay, what is it about this RBCs that makes them, why is a protein adsorption not happening on these structures? What does nature do to reduce, to not allow macrophages to recognize them? Why are they not getting cleared? Why are they, by the way, these are the only circulating cells, right? They are not adherent. They are circulating in the system. So a little bit of research showed us that the stealth property, or not being recognized by macrophages property, comes to RBCs because of something called as the CD47. Now, what is the CD47? CD47 is a protein which is present on the membrane. And what it does is it interacts with something called as the signal regulatory protein alpha, or the SIRP alpha. And this interaction happens because of the clustering on the macrophages structure. So the CD47 will interact, and it aggregates the SIRP alpha on the macrophage surface. this aggregation or clustering signals the macrophages that don't worry, this is something self, do not eat it. Okay, so that's how RBCs have been able to reduce its eating up by the macrophages. And whenever by the way, RBCs get renewed quite fast. So whenever these RBCs or the immune cells have to be renewed, the distribution of CD47 is reduced. Okay, and what happens is that this clustering cannot happen, and they can actually be taken up by the macrophages easily, and they are cleared. Okay, so this is the mechanism. Well, as I mentioned, I was not the only one looking into this aspect. There were many people working on it. And what we found out was that a lot of literature exists which talks about just taking the RBC and coating the nanoparticle with it. So, you have the nanoparticle and then encapsulate them into the RBCs and coat the structure. So they did that. People have also added CD47. So instead of adding PEG, now can we add CD47 on the surface? Now think about it. The moment I add CD47, do I know the distribution of CD47 on the RBCs? We don't. So I will not be able to cause the clustering effect, because remember, my cellular membrane or the synthetic membrane where I have incorporated CD47 cannot reassemble, cannot restructure, whereas my RBCs can restructure, right? Because they are liquid, more liquid than the polymeric particles. That is why modifying with CD47 has not resulted into successful strategies. And there were a lot of literature. People have also made RBC mimetic, where they have taken the polymer. I was just telling you, they have the RBC membrane proteins and they have incorporated that. They've shown some improvement, but then it was not the solution. So what we did was that we said, okay, fine. We are not biologists, we are chemists. Let's take the material, let's take RBCs and remove everything that is present in that, all the inside material, make it an empty bag. And then the empty bag will basically be just a lipid structure. This lipid structure, when we put it in the extruder will not know whether it's the lipid that you have gotten from the vendor or it's the lipid from the RBCs. The extruder is going to do the job, which is assembling the lipid into a particular size, right? You're basically mechanically breaking the lipid and restructuring it because you're passing it through a filter. So it's going to be very simple. As a chemist, this seemed like a really easy process, and that's what we did. So by the way, removing content from RBCs has been a very common protocol for biologists. They do that all the time, okay? And they call it as host particles. So we found protocols which was there in biology where you do hemolysis, you remove the heme from it, so they become transparent, they become colorless, and then you reseal it, incubate it with whatever. Now we said now we are putting in the extruder. Can we have synthetic lipids there? Can we have synthetic molecules there? Whatever. You extrude it with anything of your choice to give flavor to it, and then what you assemble is a small sized particle, which is made up of your RBC membrane, and the drugs will be incorporated here. The proteins will be intact, and you can now load hydrophobic, hydrophilic, different polymers, whatever you want, right? So it's very easy to do. So we did that, we made it, but then we wanted to confirm, and I'm just going to skip to this and go to, okay, by the way, before I get into that, the drugs and the dyes that we used to study this we made a conscious choice of this because we wanted to understand where is the dye getting partitioned. Is it partitioned in the hydrophobic region? Where is it? So we chose dyes which is sensitive to their environment. So if they're in the hydrophilic region, they will have a different fluorescence, whereas if they're in the hydrophobic region, they will have different fluorescence, right? So that allows us to say, where exactly is my dye partitioned? Is it here or is it over here? Okay. Then we also looked at the drug, which is basically we chose camptothecin. Now, camptothecin is a very potent drug which has been identified. It's I think it's in phase 1 trials. However, the less potent version, which is hydrophilic, is in clinical trials now, maybe phase 3 trials, and for lung cancer. So we thought this would be a perfect molecule to start working with if you're delivering doxorubicin. I mean, there is no point because Doxil is already there. So we wanted to choose something new. So after making the nanoparticles, we of course did a lot of characterization. So this is what the TEM looks like. This is the nanoparticle host where you see the bilayer, and then you start looking at where is the dye and where is the drug and all that. You start seeing this independent nanoparticle under the microscope, and then we of course looked at we characterize the nanoparticle, like the size, the charge, what happens with every extrusion. More importantly, are the proteins intact? Are the proteins there on the surface? Is CD47 there? So we did single particle tracking, and we identified with CD47 antibodies, and we identified that each nanoparticle that we had CD47 on them. Okay, and they were very stable. So there were no protein adsorption, and they were very stable. So we were very excited about it. And so the first thing that we did was to try to compare them to liposomes. Are they actually longer circulating? Because we are making it with RBCs. So this is the data for that, and you can see that even after 24 hours, we saw better, slightly better, longer circulating. And after 24 hours, if you look at the biodistribution, this side is the liposome, and this is our nanovesicles. You start seeing enhanced tumor accumulation. Okay. Which is probably because you have them for a longer period of time in your system. So yes, indeed, it was longer circulating. So you can see significant amount after 24 and 48 and 72 hours in tumors for your vesicles, whereas in your liposome, everything gets accumulated in 24 hours and slowly starts to degrade. Okay. So after confirming that, yes, indeed, it is longer circulating, we started doing all our basic biocompatibility studies. And you can see that they were biocompatible. They were not, because they were made up of RBCs. We were worried that maybe they will have heme, they'll be have toxicity to the red blood cells. We found that they were not toxic, and there were very less protein adsorption. So this is the albumin adsorption, and you can see that there's very little protein adsorption, similar to RBCs. They were immunocompatible. So we did different interleukins and different cytokines we looked at, and we saw that they did not elicit any immune response as well. Then we started, once we were confident that yes, they are being well tolerated by the system, by the host, we started modifying the system for loading drugs and doing other applications. So when we started looking at drug loading, what we found was that we have these materials. I showed you a very rosy picture where I said, everything will be taken inside. We did not see that. We saw that the drug loading was very little. And we saw that even if we loaded the drug, everything released really fast. Within 24 hours, within 2 hours, most of them is released. And some, maybe 20% is released over 24 hours. So although it's a longer circulating, if the drug is released within 24 hours, it is not going to be efficient, right? So what we did was, of course, I'm going to skip all this, and I'm going to, So what we did was that we wanted to first improve the drug encapsulation. So what we did, we formed micelles. Okay, we said, okay, fine. Now that we have a bigger nanoparticle, about 100 to 80 nanometers, can we make smaller micelles and make them more stable, and then put the micelles inside so that there is a dual diffusion layer? Okay, so we did that, and what we have here is a micellar structure which we put inside the these liposome, these vesicles, and we found that these, in fact, so this is what they start looking like now. These were very good in delivering the drugs, and they were long circulating. You can see that they were present in the tumor even after 72 hours. And you can see that in 6 hours, there was a lot of them after 6 hours, however, started to reduce in 24 hours. And then slowly, because of long circulation, and non-adsorption, it keeps clearing up. However, because it's there in circulation, it slowly eventually accumulates more in the tumor. Okay. So with this, we started looking at therapy. Can we do some therapeutic interventions? And we started looking at, we saw that indeed we were able to deliver the drug efficiently for a longer period of time. However, it was not it was not very high at this time. The cell death was just a second. We did not have this, so you can see that after 15 days of treatment, the tumor starts to grow. So this is not an optimized system yet. We saw that it is not perfect at this stage. We started looking at what is the toxicity, and we found that although the free drug was very toxic, it had toxicity to almost all the organs, our system was able to reduce the toxicity, but we found the intestine still had similar level of toxicity. So even with the vehicle, it was not completely safe at this stage. There were some toxicity that were observed this is over 30 days, okay? But still better. So we're working on improving the system more, and maybe we are sure what we're trying to do is change the drug regime. We are thinking of losing lesser dose and coming up with multiple dosage, right? So that's one strategy. We are working on that. The other strategy we thought was that what if we reduce the dose and have multiple modalities? For example, you can use chemo, you can also use radiation at the same time. So can we use dual therapy? Because what that would do is that will also reduce the toxicity of the material and the drug. So, in fact, here we were looking at the toxicity of the material, the drug, and we also looked at the toxicity of our material. We did not see toxicity because of the nanoparticle, but we saw a lot of toxicity because of the drug, so the free CPT. So we thought that maybe this delivery vehicle is safe. However, the drug itself is very toxic and we need to reduce that. So we wanted to use dual therapy. So for that, what we did was we loaded a dye which is called as ICG and indocyanine green, and it's a very common clinically known dye, and it uses near IR to generate ROS or to generate heat. So these two are two things that you could do depending on what is the wavelength that you're using. So in our structure, we try to generate ROS, which is going to, remember, because we are asking the cells to enter inside. CPT has an intracellular mechanism. So we want something that goes inside the cell and starts to kill the cells. So we wanted to have ROS generation. So we chose ICG. And what we did was that, this is called as the photodynamic therapy, if you want the common terms. So we started looking at, first we characterized the material. I'm going to skip all this, and started to confirm that the ICG is indeed present. Now, this is the detection of ROS. We started looking at, is ROS being generated? We were sure that the CPT is doing its job, but is ROS being generated, and is the ROS which we are trying to generate significant enough to cause toxicity, right? So this is basically all the studies to generate ROS, and we saw that indeed the moment we start irradiating the sample with just 3 minutes, we start some ROS generation, okay? So after all these optimization, we started looking at, cell death due to ROS, and you can see here the red cells are the dead cells. So you will see that, you start seeing more cell death if you have laser irradiation compared to just the regular without laser irradiation. It was significantly different, and that's an optimization process that we had to come up with. Here it's important to note that, we were able to get the effect, we were able to get this significantly higher effect. So this is this 2.5 micromolar CPT, which is not giving you any toxicity. It's about only 20% toxic, right? However, if you add slight amount of ICG, you see the dramatic increase in toxicity now, right? Because now they are working synergistically. So after proving this in vitro, we moved in vivo. And we started looking at, so by the way, we confirmed that the toxicity that we're seeing is because of ROS generation. So in vivo, we started looking at, what happens to the tumor, what happens to, when you start irradiating and with a laser and all that, is it enough, and things like that. What is the temperature increase in the tumor? And eventually we saw that after 12 days, we still, there was a reduction in size. But as I mentioned, it is not very dramatic. And this is also COVID time, so we were not able to optimize our dosing. So for example, you can see that by day 6, there is a retardation, and 8, there is a nice retardation. It is kind of stabilized, but then after day 8, it again starts to grow, because probably we needed to come up with a second dose over here, which we have not been able to try. So we'll be trying that. So I'm going to conclude this part. Do I have more time, or how am I placed?
Yes, ma'am. You can take another 5 minutes.
All right. Okay.
5 to 7 minutes.
I
Yes.
had more slides, but I'll just conclude this part because I'll skip the rest of it.
Yeah.
So,
7 minutes and then discussion.
Sure. I'll try to conclude just this part. So, what we've done is, in conclusion, we have these platform technologies which can be used for chemotherapy, chemophototherapy. You can use, you can do a lot of reproducible stable nanoformulations. It has, basic structure of the RBCs, which is, so it makes them very biocompatible. It can have sustained release of drugs with the micellar structure that we talked about. It has long circulation in mice, and it is more effective compared to free drugs. So where are we placed? What are the challenges that we have? Of course, we have not completed the preclinical studies. For example, we do not know the complete complement activation that happens because of these particles. The therapeutic benefits is not compared to, we've started comparing it with liposomes. We have some data on that, but it's not completely done, right? Commercialization challenges, in case we would like to commercialize this, there's a multi-step formulation. I mean, you have to extrusion, there's a bicell, it's quite complicated. Scale up will be difficult. Ethical and regulatory issues. For example, we have to take blood from the patient, and then the patient's blood, we're talking about, let's say, personalized medicine. How are we going to use it? Is it going to be stored blood? Is it going to be fresh blood? Like, a lot of questions are there which are unanswered in our research yet. There's a risk of cross-contamination from donors' blood. How are we going to make sure that there is no cross-contamination? It can fail because of the EPR effect in the clinic. Lot of, for example, all the inflammatory regions has high interstitial fluid pressure. And because we have reassembled this material, it can actually be very unstable in those high pressure areas. We have not studied that, right? There could be dense extracellular matrix. So maybe it won't be able to penetrate. Remember, there is lack of RBCs in regions, if you have like some sort of not a tumor, but just a protrusion even on your skin, these masses actually do not have RBCs in that region, right? They don't have, that's why they have these white blood cells. Even oxygen cannot penetrate through. So you get pus formation. So how are these nanoparticles going to go there, right? So these are going to be some challenges that we need to address before we take it to the clinic. Big problem, if you want to take it to the clinic, sterilization. How are you going to sterilize these materials? These are biological materials. So autoclave and all those things will not work. There could be particle aggregation, there could be degradation, a lot of things can happen. So it's going to be very, very challenging. Of course, why are we not doing all these things when I'm aware that these are the things that is needed for translation? We are limited by inadequate preclinical models. For example, I do not know whether a mice model a rodent is a better model. I do not have access to a swine model or some other model. I do not know how to look at the innate immune response. I don't know how to study the complement activation, which models to use. And, so it's a lot of research from different areas that needs to go in this field to actually take this material to the next level. So with that, I'm going to skip all of this because the next part was talking about how, so this is, what I've spoken to you is one aspect of our drug delivery research, which is addressing the protein corona formation. Remember, I had 3 things, which was, other one was the intracellular interactions, and the third one was the ROS generation. So intracellular interactions, I'm just going to show you quickly. There's a lot of report talking about if you have a spherical particle which enters the cell, but it has, say, a very rigid structure. It won't be able to interact. There will be sterics, right? So suppose you have a protein and you want your nanoparticle to interact with it. If you have them, this interaction cannot happen because there is steric. So, and you attach a small protein molecule or a small antibody or a small nucleotide for RNAi delivery, it is not going to be able to attach, right? It is going to have sterics. But if you make the nanoparticle slightly softer or fluid, then what will happen is it will change the shape, and because of the change in shape, you will reduce the steric, right? So there was a report when we were thinking about it. There was a report in 2017 in Nature Communication which talked about exactly this, and this becomes extremely important in RNAi. For those of you who are familiar, the nucleotide is just 21 nucleotides. So imagine this small interfering RNA. You have a 20 nanometer particle, and I have a picture. This is what it looks like. You have a 20 or 100 nanometer particle with a strand which is 21 nucleotide. It has to interact with an ego protein which is 20 nanometers. How is this interaction going to happen? So now, if I had to come up with a nanoparticle which is going to be useful for RNAi, I just told you, either I make this really small or I make it really flexible, right? Otherwise, it won't work. But if you look at the literature, you will find that literature has, gold nanoparticle, mesoporous nanoparticle, hard particles working well. So our lab actually spent a lot of time. So this is the argument. You have either a small particle, a soft particle. So we did a systematic study. We made small, soft, large, hard, and things like that, keeping the surface the same. So we developed a model system and started looking at how the interactions happen. And of course, we characterized it. And then I'll just show you, we also developed an in-house assay where we're trying to look at these interactions and quantify them. Because quantification is important. How do I know that it is interacting? Because remember, even if slight interaction happens, it is going to show me the end result of silencing, right? So, and that's what literature is seeing. So how do I know, how do I quantify this interaction? So we developed an assay here. And ultimately what we said was that the proposal that I gave to you earlier of a flexible particle actually was not true. We were biased at that time, but what we identified was small and a soft particle was the best. The second best was a large and a soft particle. So the size actually did not matter. The third best actually surprised us was a large and a hard particle, which, think of a 100 nanometer mesoporous particle, which was very interesting. Then was our small and hard particle. So the small and hard particle was the worst, which is not what you would imagine, right? So we then gave some explanation for it, how this is happening. We forgot that if you have a large particle, you have more surface, you have more area for the protein to interact, and it creates something like a flower. You have a core and you have these small proteins sticking on the surface, but it doesn't happen with a smaller particle. So the small hard particle was the worst. So that is something which we should avoid if you want to do RNAi. So our lab was the first one to actually give these design rules in the field, and we were quite happy about it. So that's one. Then we have also addressed the ROS issue. I'm going to skip on this. Just wanted to highlight that there were a lot of literature which talks about nanoparticle, and they say that it's a biocompatible material. And if you look at the toxicity, 50% of the cells were dead. So they show that 50% there was less cell death. But to me, as a researcher, 50% cell death is also toxicity. So we came up with a method. What we did was the ROS, we can reduce ROS formation by just putting them into a polymer, right? So think of a surface which quenches the ROS. And that's what we did. So here we created these nanoparticles where we can have the carbon dots embedded in them, and the ROS can be quenched by the polymer. And this allows you to actually, so this is like a Lay's bag and you have some chips in it, right? So imagine, so this is the picture. So imagine your chips in a really big swollen vacuum packed bag. Nothing happens to the chips and the packet absorbs all the shock, right? So that's exactly what it does. The polymer absorbs it. Now, remember, we are not the first one to put polymer on it, right? People have been putting polymer quite a lot. What was the problem? They would just coat the nanoparticle with the polymer. It's not enough to absorb all the ROS. It is not enough to quench entire ROS. So we need more for absorbing that shock, okay? So that's kind of what we showed, and we showed that indeed the ROS was quenched, and this can be used for drug delivery and things like that. So I'm going to stop here. Of course, you can read up all our publications in case you're interested. We have some patents on these strategies as well. And with that, I would like to thank my excellent lab. I've had a lot of students from MIT as well. We have Simran, who's working with us. She's my PhD student, this one. She is a student from MIT. Even Supriya is a student of MIT. So I have a couple of students from MIT. This work that RBC work was Sahil Malhotra, and he has now moved on to do his postdoc in the US. And I couldn't do anything. All this work is not me. I'm just a ambassador for our lab. And my students do all this hard work, and they've been all the ideas, crazy things that I tell them, they very patiently listen to me and start doing all these crazy things. Sometimes I put them into these areas without any precedence. For example, the RNAi concept that I told about, we had to develop a lot of things for our lab, like the assays and all that. There were no precedents for it. There were no literature about this. So it's challenging for the student when they're doing it, Of course, the funding agencies have been very, very generous to our lab. I was supported very well with my institute. IT Delhi has been supporting me with space and of course with funding as well. DBT was one of our first supporters with IYBA scheme, and now with Janki Amal and DBT Nanobiotech. In fact, this RBC work was supported by DBT, and I'm thankful to them for supporting this crazy idea of taking blood from patients and making nanoparticles out of that. And then DBT Nano Mission has supported our siRNA work. Again, when I presented, they thought that, why am I even interested? There is no precedence and all that. So they kind of gave me a tough time, but I'm very glad that they've supported these blue sky ideas and these fundamental studies as well, which are important for developing the field of nanomedicine. Recently, I have gotten the Sir Power Fellowship, which is, again, I'm very thankful to them. This gives me visibility nationally. And, this is given to select few women researchers. And this is important for highlighting how women are also doing amazing work. And you can see that my lab is also, I believe in supporting and mentoring women a lot. And so with that, I would like to thank you all for giving me this opportunity and patiently listening to our work. Thank you.
Thank you so much, ma'am, for such an excellent talk and so informative.
Thank you.
So there are a lot of, I think, question. Chinmay, you can take the question. First we discuss, then we'll ask from the panelists.
Sure. So one question I can see is from our faculty, Dr. Nidhi. So she's asking, how do we test for hypersensitivity reactions?
So in vivo, you have various models where you can test for hypersensitivity reactions. So it depends on what applications you're looking at. For example, the immune response, because this is going to be taken up in vivo, like intravenously, right? So we are planning to have an intravenous thing. So what we're looking at is different cytokines which are upregulated. Okay, so the interleukins, the TNF alpha. So we inject the sample, we draw blood, and we look at what are the cytokines. The hypersensitivity in the tissue region can be identified by sections. So you can take sections and you can look at are macrophages present, what kind of cell infiltration is present, and things like that. So there are different models of doing this.
There is another question by Anu. She's asking, ma'am, do you have cell culture facility in your lab, or you do on cancer lines only?
We have a cell culture facility in the lab, but we've not started working on primary cells. We have collaboration with ILBS where we do primary cells. We have collaboration with AIMS. In fact, this work was done with Sujata Mohanty at AIMS, where she helped me use the live animal imaging facility and things like that. So we have various collaborations which we use. I mean, you all are aware of all the facilities at IT Delhi. We are good, but probably not complete in any aspect. So we do have some lack of facilities here. So but that has not stopped us. We've been trying to collaborate with a lot of people. We have collaborations almost everywhere. We have with ILBS, AIMS, THSTI, RCB, everywhere.
Okay, then I would like to ask the panelists if they have any questions for ma'am.
Yes, Chinmay. Ma'am, I have two questions. One is, as you have shown the small and soft, that is the best one in terms of. Here, this soft is polymerase or any emulsion type, micellar structure that can be considered as the soft.
Yeah, that's a very good question, Dr. Bhattacharya. So, so soft for me for this particular study was a polymeric particle. And I'll tell you why we did not use a liposome. Liposome are also kind of soft, right? The reason we did not use is because we did not know, honestly, we do not know how much force is this interaction putting, right?
With the
So,
cell.
yeah, with the cell. So maybe it's very little, maybe it is not enough to break the liposome. However, there is chances of breaking the liposome because of the deformity. The structure could break. It's an unstable structure. We didn't want that to affect our results. Because what we started looking, we want the structure to be intact. And that is why we used a cross-linked polymer.
Cross-linked polymer, right. Depending on the cross-linking, you can change the strength.
So we did this, we identified the Young's modulus of all of them. That's how we quantify them to
mechanical strength,
medium, soft, and things like that. Yeah, so then the other aspect was that you want your hard nanoparticles and the soft nanoparticles similar, because you can't compare apples and oranges. Remember, the surface becomes very important. So if I take gold nanoparticle, it will have citrate, whereas my polymeric particle will not have citrate. So then the interactions are actually not same. So what we wanted was, we want the same surface, right? So that is why even the hard material that we use, we polymerized the same polymer that we use for the material, so that the cell does not understand that it is a different, it's just a mechanical property which is different.
Yes. Well, just check the mechanical properties.
Yes.
Another question I have, ma'am, regarding the RBC. So what you have used the RBC for the drug delivery. So this source of RBC, it is something artificial or natural blood?
Natural blood.
Natural blood.
So we got it from blood banks.
Yes.
We had to get an ethical approval. These were human bloods. We had to get an ethical approval. So we got it from blood banks. We also got it from, at the IT hospital, like fresh blood. Sometimes, because we wanted to compare, we did not see a difference, huge difference between blood bank samples and the fresh samples. But we've not done thorough studies on what proteins, because remember, we were very focused on CD47 initially. So we were just looking at whether the CD47 is retained or not.
Ma'am, if you make some formulation with these RBC for drug delivery, what will be the stability in this formulation?
Yeah, so for us, they were similar to liposomes. So they were stable for a week, but we would have to make it. And honestly, we made it every time we did it, because we didn't want to, because you don't want the data to be, because this is the first time doing it. So we made fresh samples every time we did these experiments. The only thing we maintained was the CD47 presence. We would confirm that every batch, the size and the charge.
Right.
So these three things were key, and we would do it for every sample that was used, because we wanted to make sure, because the charges is a natural material, so there will be variability. So we wanted to make sure that only the batches which had similar charge would do that. Fortunately, after some time, it was optimized and it gave very reproducible particles.
Thank you so much for your nice presentation. If any other panelists have any question, please come with this.
Hello, Dr. Singh. Although I don't belong to this field, but I must congratulate you on your enormous and excellent work. Especially whatever you've presented is, it's amazing. It was a pleasure to hear you. So I was wondering, when you talked about these, you modeled the different, like small, soft nanoparticles, large, hard, and all these things. So have you been doing some simulation before you go for actual experimental trials, or just like you hypothesize and just, okay?
Yeah, honestly speaking, I'm not a theory person, so I don't know how to do simulations. I did run, door to door, asking my collaborators and friends and experts to help me out. But remember, this is, science is a very interesting area. I believe we are all very selfish because we do things which interest us, and that's why I think we like our profession. It's uh, so for other people, this was not interesting problem. For me, this was very interesting. For
But
other
your
people,
crazy idea is amazing. I must
yeah. So I mean,
admit.
for me, I thought that
What you say crazy is not actually crazy.
no, but that's because I'm telling you like this. I'm telling you a story, so I'm making it interesting, right? That's my job. But when I started working on it, people said I had people asking me, why do we even care? As long as they're working, why do we care, right? So many times we do not want to understand why it is working, and that's an engineering versus a science philosophical difference. We want solutions. So many places when I went there, they said, well, the hard particles and the large particles are working well. Mesoporous silica nanoparticle, gold nanoparticle, liposomes have been shown efficient RNAi, right? So why do I care about understanding which should be the perfect particle for this application? For me, that was important as a materials chemist because now
Even I understand that these three challenges, what you have posed, are actually probably the major limitations that is restricting these nanoparticle based drug delivery into a commercial thing.
Absolutely. And unless we have enough data to understand these mechanisms, I believe that, there won't be, we keep focusing on applications a lot. We never look at these fundamental studies, which are very important. And as a chemist, only I can take up these studies, because I can modify the material. The biologists are not able to do this because they will do the biology well, but they don't know how to modify the material. How do they make a soft versus a hard particle? I mean, only I can do that. Those polymeric particles, those cross links and other things, only I could do it. So that's why I thought that my lab would be the best one to pick this problem, and that's what we did.
Thank you. Excellent work.
Thank you. Thank you.
Ma'am, there is one
Chinmay,
last
I think
question.
there's one more question. Yes.
Yeah, so it's from the same participant asking how you check the drug is properly encapsulated in the vehicle. Is there a method or technique to follow?
Yeah. So the drug encapsulation, you can of course do release and all that. That's a very standard method. But what I did not tell you about this drug, camptothecin, is that it also has a fluorescence. So this fluorescence is very low, but it allows you to track it. It allows you to. So all the things that we've used in our nanoparticle has distinct emission peaks. Okay. So it allows us to understand where exactly is it located. And this is also environment sensitive. So the CPT, if it is in a hydrophobic region, it will have a distinct fluorescence. The ICG is in near IR, so that's a different wavelength. And the other one, the DIM, that has a distinct red emission. So we were able to, there were three different regions, there 3 different molecules, and they all had distinct emission and excitation wavelengths. So we were able to monitor where they are.
Okay, ma'am. I think there are no more further questions. So we can close the session now for lunch. And thanks,
Just
Dr.
a
Neetu.
quick thing. I think someone asked about there is a technique to follow. We've published all of this, so you can go read up our papers. You'll find all the details there. So we've published almost 5-6 papers on this now. So you'll find them there.
So please do check out Dr. Neetu Singh's profile for further answers. And I thank you, ma'am, for this wonderful talk and this unique
Thanks a
problem
lot,
that.
ma'am.
Thank you for inviting me. Thank you so much for inviting me.
And we want your lecture in physical mode also.
Oh, absolutely. I would be very happy. I love to teach.
Yeah.
So I would love to interact with the students.
Yeah.
Okay.
Thank you
All
so
right.
much for
Bye.
your
Bye.
time and nice time.
So now I close the session for lunch. So we'll be meeting at 2:30 p.m. Followed by the other series of talks. And thank you very much, everybody, for listening to this session. And I'll see you all at 2:30 p.m. Thank you.
one more experiment related to all our samples, like single, co, and triple dope samples, and realized that the sheet resistance of the triple dope sample is found to be around 2.8 into 10 to the power 3 ohm per square, which is less than the other samples, zinc oxide sample. The stability of the sample, which is another plays a crucial role. It tested about for 80 degrees temperature and high humidity. And we found that the triple dope sample is getting highest properties in comparison with the single and co-dope samples. That is, it has high transmittance, high conductivity, as well as high stability, which is very beneficial for the optoelectronic application. So in conclusion to my work, first one, I have prepared the samples using physical method and chemical method. So the first physical method prepared sample gives us optimized value of 5 aluminum 5% doped zinc oxide films for sufficiently low thickness, exhibit high transmission, low resistivity, making them excellent candidate for the novel optoelectronic device application. Then after moving for the chemical preparation method, we have prepared aluminum, gallium, indium doped zinc oxide films using chemical co-precipitation method and found the transmission highest for the gallium doped zinc oxide and conductivity is maximum for aluminum doped zinc oxide. In overall, the highest conductivity, transmittance, and stability is achieving for the triple dope zinc oxide samples. So overall study confirms that triple dope zinc oxide sample possess all the required properties for the optoelectronic devices and makes it suitable for better TCO material for all optoelectronic devices. In the future work, we can optimize different combinations for the use of this TCO material in the optoelectronic devices by making its different concentrations values for triple dope zinc oxide sample, and we can tune this optoelectronic properties for all the optoelectronic devices. Here is the acknowledgement. I owe a special thanks to my PhD supervisor. With her, I have performed all these experiments, Dr. Richa Krishna, and to my co-supervisor, Dr. Ramjana Chaudhary, and here is showing my lab group. Thanks. I very thankful to my lab group. My sincere thank to the advisor, Dr. Director AINT Professor Upasina, and all faculty members of AINT for their persistent praise and assistance in providing me the platform to present my work in this workshop. Thank you so much, sir. Thank you, Amity Institute of Nanotechnology and UGC DA for providing me the necessary facilities. Thank you.
Thank you, Mr. Saxena, for giving an elaborative talk on doped ZNO, zinc oxide nanoparticles and their application and their various characterizations. So I would like the participant to please write your questions for the Mr. Saxena in the chat box. Meanwhile, if the panelists have any, if the panels have any questions to the Mr. Saxena, they can directly ask to her. I guess there is no question from the panel side as well as from the participant side. We can move ahead with this session. So I would like to invite Dr. Arpita Bhattacharya ma'am to give a summary of today's session.
Rohit?
Yes, ma'am. Yes, ma'am. You can give a summary, ma'am.
Right. For previous session, no?
Yes, ma'am.
In previous session, we had 5 speakers. The first speaker was Dr. Pika Jha. Her title was topic was development of CNT based sensor for environmental pollutants. So she basically described the CNT based sensor, natural nose, like on descriptions, compare between natural nose and artificial nose kind of sensor, and she described in detail the manufacturing or the designing of the sensor, then their recovery rate, detection limit, and different type of gas sensor like ammonia, carbon dioxide, carbon monoxide, nitrogen dioxide, etc. Along with this, she described how to detect the mixture of gas, like say ammonia and nitrogen dioxide. Then she mentioned that functionalization improved the selectivity of gas sensing when there is a mixture of gas. Other than this, she also mentioned about the sensing of some chemical warfare agent by using the CNT based gas sensor. Second speaker was Dr. Bidhan Das, Deputy Director and R&D Head from Indian Institute of Packaging. His topic was latest trend and innovation in food packaging. He described different type of packaging system, level of packaging like say primary, secondary, tertiary level of packaging. Then he described about the nanomaterial based packaging system like active packaging and intelligent packaging. He showed a number of examples like say Tetra Pak, like we use the fruit juice, fruity, using the Tetra Pak. So Tetra Pak is nothing but several layer of the packaging system which have different function of individual layer. Other than this, he mentioned the barrier packaging system, oxygen scavenging, or other type of gas scavenging packaging system. So elaborately, he described different type of consumer goods and their packaging. Next speaker was Dr. Aviru Basu from INST Mohali. His topic was design and development of MEMS-based sensor for rapid detection of trace analytes. He described about the detection system depending on the cantilever design. He described fabrication of cantilever and the different application of the cantilever, like say, sensor development, point of care diagnostic system. He mentioned about the synthesis of reduced graphene oxide, MWCNT, and alpha iron oxide composite and their characterization. He used this composite on this cantilever for the detection of chloroform. So at different concentration, he showed the deflection of the cantilever with the variation of the concentration of the chloroform. Other than these, he also mentioned this similar type of composite can be used for some other cholesterol diagnosis system. Our fourth speaker in the morning session was Dr. Sumant Upadhyay from Amity Institute of Nanotechnology. His topic was nanoscale metal oxide 2D heterostructure for photochemical water splitting, a DFT study. Here he mentioned about various metal oxide structure interface, cerium oxide, cuprous oxide, silver dope cuprous oxide, iron dope cuprous oxide, etc. He mentioned about the mechanism, how the splitting occurs. He also described the requirement and trade-off for an efficient semiconducting photo electrode material. For this electrochemical method, electrode is very important. And he described some simulation study, mentioned about Schrodinger equation, density functional theory, and especially focused on the splitting of water for the hydrogen generation. The last speaker in today's morning session was Dr. Neetu Singh from IIT Delhi. Her topic was engineering new materials for drug delivery, a chemist's perspective. Here, Dr. Neetu mentioned different type of drug carrier system, drug delivery system like liposome, micelle, CNT, gold, etc. And he focused on the different problem to translate this type of delivery system into clinical study. So she mentioned that we need to understand the biological interaction of this nanocarrier with the cell. She also mentioned the new area where the RBC of our blood, human blood, which can be utilized for the delivery system. She also mentioned that shown some comparison between the soft and hard and small and large carrier system, and have shown that the small soft carrier system is the best for the drug delivery. So she has given a wide insight of the drug delivery system with the nano carrier. That's all for the first session. Thank you.
Thank you, ma'am, for summarizing the morning session and summarizing today's talk. Now, I would like to invite Dr. O.P. Sinha, HYF of our department, for the validatory session. Sir.
Yes, sir. Rohit. So who are the other member in the validatory?
Sorry, sir.
Who are the others member in the validatory session?
Sir,
Dr. Mittal, Dr. Anu, Dr. Nidhi.
I'll ask Ranu ma'am once.
Should we start now, Dr. Mittal? Dr. Mittal, should we start now?
Yes, sir.
Okay. So, dear participants, that's come the end of your 4-day value-added course workshop on smart nanotechnology for the societal applications. So I welcome all of you during this validity session, and it is really a sad task to start the validity session, but it is not a end of the learning. It is basically beginning of the new collaboration and discussions. So dear participants, esteemed speakers, resource persons, ladies and gentlemen, very warm good afternoon to you all. We reached the end of the 4-day value-added course workshop on smart nanotechnology for societal applications, which was between June 27 to 30th, 2022. And it is my pleasure to welcoming you all. Instead of saying end of the 4-day deliberations, I say it is a start of new beginning in terms of the new collaborations and the discussion. However, it is also a privilege and an honor to be interested with such an undertaking at the gathering of such eminent people from different parts of the country in the field of science and technology. This workshop is a great example that how people can use the nanoscience knowledge for the societal benefit and expand the research collaboration, and it will probably be a day or two before one can consolidate our perspectives. There is indeed plenty to reflect upon, and if this is anyway enhance our individual and collective contribution to meeting the existing challenges of the society, then this workshop can truly be adjusted as successful. As we have heard over the past 4 days, there is a plenty of opinion around meet our need for generation to come in terms of the characterization, in terms of the engineering, to the diagnosis, using the nanomaterials and the nanotechnology. I am sure we have all benefited in some or another way from this workshop. It has been emphasized that with the technological advancement and the breakthrough being critical in supporting this process, namely in finding new fields, capacity expansion program are well underway. The view expressed here must be disseminated to the wider readership and audience, and clearly this task has been in the very capable hands. Ladies and gentlemen, looking forward to seeing you again when we have reconvened to discuss another topical theme. Thank you very much once again and welcoming you in this elected session. Thank you.
Thank you, Dr. Sinha. Thank you, Dr. Sinha. So, thank you, Dr. Sinha, about this validity. You nicely described this workshop and purpose of this workshop. So I will vote of thanks. Ladies and gentlemen, so we are almost ending the 4-day journey of togetherness. All these 4 days have been so remarkable. I begin with by expressing my gratitude to our very beloved founder president, Dr. Ashok K. Chauhan, sir. We know the immense interest you have shown towards this event and your fascination for our institute. So we are also thankful to your blessings and encouragement. We are equally thankful to our dynamic chancellor of Amity University, Uttar Pradesh, Dr. Atul Chauhan, who believes on us and encourages to dream big so as to achieve big in life. Sir, we express our profound gratitude to you for being our inspiration. Yet another big pillar of strength is our Vice Chancellor, Professor Balwinder Shukla, who continuously thrives and inspired us for perfection and discipline. We thank you, ma'am, for the bottom of your heart for your continuous support and blessings. My deep gratitude to Professor Sunita Ratan, Dean Science and Technology, to be a part of this conference. I must mention our deep sense of appreciation to Professor J.S. Sodi and entire IT support and technical team, especially Mr. Mobin, Mr. Puneet, Mr. Arvind, to really make this virtual event progress without any glitch. Now let me take the pleasure of thank all the eminent speakers in this workshop who accepted our invitation and gave such enlightening talks in specific themes. Kindly accept our gesture of appreciation from entire Amity family. I also thankful our institutional young achievers for excellent presentation of their work during the workshop. I will also like to convey deep appreciation to all the attendees of the event who have done such a great number. It is your overwhelming participation that has rendered success to event successful. Thank you so much. Now it is time to cheer our young volunteers who would I would definitely like to take their names. Rohit Sharma, Pooja Bhattacharya, Abhyavartin, Monica Jaiswal, Sapna Balyan, Kirti Saxena, Chinmay Shukla, and Singika. So it is entire team. I am highly thankful to them to make it successfully organized. I am also happy to express appreciation to our staff members, Mr. R.N. Joshi and Mrs. Shrija Sanjay and Mr. Lalit Yadav for their support. I also express my sincere thanks to my colleagues for their timely, wholehearted support for entire event. All of you have genuine effort in coordinating and summarizing all this technical session. Thank you so much. And then, of course, my huge appreciation to my coordinators of the event, Dr. Anu Nayak and Nidhi Chauhan. Thank you. May not be right word to convey to you. In fact, my vote of thanks for this event today, all of you, is on behalf of them. And finally, it is the time to acknowledge the point source of the workshop, Director of our institute, Professor O.P. Sinha. He encouraged and motivated us for the workshop and have been with us at every stage of planning and execution. Thank you so much, Professor Sinha, for being the backbone of this event. With this, I am on the behalf of my coordinators, Dr. Anu Nayak and Dr. Nidhi Chauhan, thank you all to make this workshop a grand success. Thank you so much for this event. So we will now, there will be national anthem to finish this event. So
Thank you, sir, for giving your enlightening word for this towards the end of this session. Now, I would like all the participants, organizing team, to join us for national anthem. So, should I share my screen for the national anthem? Is it visible to everyone?
no, we not sharing, not, yes, now it's coming.
Please join us for the national anthem.
Thank you all.
Yes. Rohit, and share the
Shall I
screen.
close the session?
I haven't shared this.
Yes, Mr. Ji, link has been given to the participants.
Rohit, unshare the screen. Yes. Form is there in the chat box. So
Okay, then, Arvind, you can close the session.